Astronomers at the solar system's frontier are reporting urgent developments. The entity known as 3I Atlas has ceased acting like an ordinary comet. Just recently, experts observed this visitor from beyond our system entering a zone within 2 astronomical units from the Sun, where it started to gleam with an intensity well exceeding forecasts. The surrounding envelope has expanded to reach halfway across our star's width. Its radiance has taken on a disturbing verdant hue. Even more strangely, a tail has formed on it, oriented straight at the Sun, an occurrence that defies all known physics. Hurtling toward Mars with incredible velocity, scientists confess they remain baffled by the phenomena unfolding. The timer for its closest solar approach is now active. Hour by hour, this extraterrestrial traveler appears increasingly unlike a typical comet and more akin to an enigmatic puzzle from the cosmos, insisting on resolution. Remain with this evening's investigation through to its conclusion to discover the ramifications of this unfolding event for our prior assumptions about the universe and the consequences when chemistry from afar stirs to life. Section 1. Expansion and increased luminosity are evident. Data remains truthful, regardless of how it challenges comprehension. During mid-September 2025, those observing 3I Atlas detected an ominous anomaly in their records. Readings of illumination started surpassing anticipated patterns, escalating from the projected level of 15 or 16 to a surprising 12 to 14. To clarify the inverted scale of stellar brightness ratings for newcomers, this marks a profound alteration. Consider this analogy. Ratings for magnitude decrease as visibility improves. The lower the value, the more luminous the body. A reduction by merely 2 units indicates the body is emitting 6-fold the anticipated illumination. Yet this shift lacked gradual progression. Instead, it surged with momentum. Among enthusiasts who follow these sky rovers, the Cobb's repository for comet sightings started registering points that rose persistently beyond the typical incline forecasted for a comet heating under solar influence. Observations from terrestrial vantage points verified the pattern. 3I Atlas surpassed all simulations experts had devised for its path inward toward the Sun. The pivotal shift occurred when the body ventured within roughly 2 astronomical units of the Sun during early to mid-September. To provide scale, a single astronomical unit equals the span between Earth and our Sun, about 93 million miles. Positioned at 2 AU, 3I Atlas lingered at double our separation from the Sun. Nevertheless, a core transformation took place. The escalation in brilliance proved not merely unforeseen but intensely worrisome. What might provoke such a sharp rise in glow? The prime theory points to ices that are volatile, including solidified carbon dioxide, water, and unusual substances embedded in the core. Originating near a distant star, as the Sun's rays grow stronger, these elements avoid simple thawing. They burst from solid state into vapor, hauling along particles and fragments while forming broadening veils that bounce solar light our way. Yet this aspect warrants attention. Abrupt spikes in visibility frequently indicate precarious states. Bodies like comets undergoing abrupt gas releases risk breaking apart, yielding several fragments or dazzling arrays of rubble. They might also deplete their reactive stores swiftly, resulting in swift fading. That 3I Atlas is intensifying quicker than projections anticipate implies we observe mechanisms beyond astronomers' grasp. No grounds exist for widespread alarm across planets. That said, NASA verifies 3I Atlas will hold a secure gap coming no nearer than 1.8 astronomical units to Earth, almost double the reach to our Sun. The concern avoids impact risks. It centers on understanding. Perhaps we witness a relic from interstellar voids, transforming essentially before our eyes as it charges into the solar system's core regions. Ponder the consequences. This body coalesced within the rubble ring encircling a remote star, potentially hundreds of light years distant. It arose from substances untouched by our Sun's heat, unexposed to the unique environments that molded the objects, originating from our local stellar vicinity. For the initial occasion throughout its lifetime, this entity is facing the harsh radiative conditions within the core regions of our Sun's domain. Such a dramatic increase in luminosity may indicate the activation of chemical reactions that lay inactive over spans of millions or even billions of years. Unusual frozen compounds, which endure steadily in the extreme cold of interstellar voids, could be undergoing sublimation right now for the very first time since their formation. We might be on the verge of observing the exposure of molecular markers hailing from a distant stellar realm, kept in immaculate state while traversing the Milky Way. This schedule adds a layer of pressing importance. 3I Atlas is nearing several pivotal moments that will shape the insights astronomers gain from this singular interloper. On October 3rd, it achieves its minimal distance to Mars, just 30 million kilometers away. This proximity allows probes circling the crimson world to possibly detect features undetectable from our planet. Toward the end of October, precisely on the 29th to 30th, the comet attains perihelion, drawing nearest to the Sun at roughly 1.36 to 1.4 AU. At this point, the narrative shifts to a concerning development for ground-based watchers on Earth. As 3I Atlas draws closer to its solar rendezvous, its location against our celestial backdrop edges perilously near the star's blinding radiance. Spanning from the start of October until the beginning of November, the comet passes into what's known among stargazers as superior conjunction, a phase where the Sun's intense light renders viewing from terrestrial sites virtually unfeasible. Consequently, the height of activity for this extrasolar guest, the instant when solar warmth peaks and the comet's essential character could come to light, will largely evade our direct sight. We shall have to depend on the automated sensors of probes scattered across the heliosphere, especially those around Mars, to capture what may prove the grandest exhibition of alien molecular dynamics ever seen by humanity. The ongoing rise in brilliance implies 3I Atlas will not pass perihelion without fanfare. Recent sightings suggest a body invigorated by its brush with our Sun, perhaps ramping up to explosive releases that might expose hidden aspects of its makeup and form. Yet, will such disclosures happen amid the period when our planet's scopes are overwhelmed by the Sun's luminosity? Findings from September's viewings depict an entity undergoing change. Brightness readings surpassing expected trajectories indicate that 3I Atlas is evolving into a form distinct from its state during the extended voyage across interstellar expanses. The core issue remains: does this alteration signify standard cometary responses in an unusual specimen, or does it herald a completely novel phenomenon compared to our encounters with extrasolar arrivals? Shortly ahead, we shall delve into the reasons behind this body's coma stretching beyond feasible limits, the oddity of its tail directing sunward rather than outward, and the way its latest turn to a ghostly verdant hue could hint at molecular reactions unseen in any prior interstellar guest. Enigmas are proliferating at the same pace as the luminosity data ascends, yet prior to that, grasping the essence of this phenomenon is essential, since 3I Atlas transcends the ordinary comet. It stands as merely the third verified arrival from beyond our stellar boundaries, and its conduct is swiftly demonstrating that every such wanderer adheres to unique principles. Part 2. Discovery and Classification. The tale of 3I Atlas originates atop a Chilean peak, where automated scanners survey the nocturnal heavens with robotic accuracy, surpassing that of mortal watchers. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, spotted a dim streak of illumination shifting amid the fixed stars. At first, logged as merely one more small celestial fragment, this routine detection was poised to profoundly alter our comprehension of objects from beyond our solar system qualify as interstellar, not merely due to their distant origins, but through the undeniable physics ensuring they escape permanent capture by the Sun's gravitational pull. 3I Atlas traces a hyperbolic orbit, the kind that demands such immense energy it slings the body past our star on a one-way journey into the void, with no chance of looping back. The equations governing its path leave no room for doubt, confirming that its speed overwhelms the Sun's hold, propelling it onward indefinitely. The label 3I Atlas carries layers of meaning in itself. Here, I signifies interstellar, and the leading 3 marks it as merely the 3rd confirmed example in all of recorded history. Its forerunners, 1 Oumuamua, spotted in 2017, and 2 Borisov in 2019, each stunned experts with traits that resisted straightforward classification. In the same vein, 3I Atlas upholds this legacy of cosmic surprises from afar. Spotting these wanderers proves an arduous task, as the detection methods highlight. The Atlas setup runs from the Riardo Observatory amid Chile's Atacama Desert, integrated into a worldwide effort to flag asteroids that might threaten our planet. It snaps repeated shots of fixed sky patches across brief intervals, then deploys software to pinpoint any shifts amid the fixed stars. That fateful July evening, 3I Atlas showed up as a mere dim blur, hardly set apart from the swarm of asteroids, comets, and orbital junk crowding the solar system's core. Yet, archival shots prior, captures predating the formal find uncovered that 3I Atlas had lingered undetected in data archives for weeks, its true nature overlooked until then. Such late identifications often plague interstellar finds, which mimic asteroids at first glance, before unveiling the hazy envelopes and trails signaling their cometary essence. Right from the start, evaluators noted a subtle glow encircling the core, hinting that 3I Atlas transcended a mere stony hunk. These nebulous halos form as sunlight warms the surface, vaporizing frozen compounds into swelling clouds of vapor and particles. Detecting such activity at a remove, 3I Atlas lay past 3 astronomical units at detection pointed to reserves of fragile substances able to vent gases despite the chill in the system's fringes. Word of the find rippled across the field of astronomy, drawing bigger scopes to track the intruder. In July, the Hubble Space Telescope gathered sharp views, joined by data from Chile's Very Large Telescope and various earthbound sites. Deeper probes exposed a far more intricate visitor than the debut glimpses implied. Gauging 3I Atlas's dimensions stays elusive, a typical hurdle for dim, remote targets evading precise sizing. Hubble's later August refinement pegged the core at 0, 3 to 5, 6 kilometers across, underscoring the challenge in isolating the dense heart from its gassy shroud. This ambiguity in scale influences estimates of weight, makeup, and resilience against the sun's fierce blaze as it nears. Velocity assessments, however, offer sharper insights into its wild profile. Hurtling along at about 130 km/h, or roughly 58 kilometers, 3I Atlas outpaces any native solar system traveler by a wide margin. By contrast, our planet circles the sun at a leisurely 30 kilometers. As gravitational tug hastens it to closest approach, the pace could climb to 68 kilometers, exceeding 150,000 prots. These blistering rates. To highlight the extraterrestrial essence of this cosmic intruder, consider that no entity forged in our solar system could attain those velocities organically, devoid of gravitational boosts from slingshot orbits near colossal worlds. 3 Atlas bears the momentum imprint of its voyage from distant stars, amassed across countless millennia navigating the Milky Way, amid pulls from stellar gravity and the swirl of galactic dynamics. Such verified wanderers from interstellar voids remain exceedingly scarce, rendering every instance invaluable to scientific inquiry. Prior to 2017, experts relied solely on conceptual frameworks to anticipate the conduct of such travelers amid their vast treks. Oumuamua upended numerous preconceptions through its cigar-shaped form and enigmatic thrust beyond gravity's grasp. 2 Boris presented a more typical cometary aspect, yet unveiled molecular makeup alien to our system's inventory. Presently, 3 Atlas contributes a further datum to this meager archive, with initial signs hinting at distinctiveness matching its forerunners. This entity's actions disrupt established theories afresh, especially via its surprisingly expansive envelope and erratic shifts in luminosity. Every such far-flung arrival appears to embody bespoke physical and compositional principles, implying the Milky Way teems with greater variety in the genesis of minor celestial forms than once conceived. Beyond mere validation of extrasolar provenance lies the categorization effort. Scholars need to ascertain if 3I Atlas embodies an asteroid-esque form, a comet, or an altogether novel category. The evident envelope points firmly to cometary traits, though the precise blend of vapors and particulates, discerned via spectral scrutiny, will clarify its genesis and maturation within the stellar cradle of its origin. Far from an indigenous comet propelled sunward from the Oort cloud, that remote depot of frozen remnants sporadically dispatching envoys to our system's core. 3I Atlas coalesced orbiting a foreign sun, drawing from substances shaped by alien thermal regimes, compressive forces, and reactive milieus unlike our local stellar domain. It stands as a pristine specimen of world-building dynamics, unfolding parsecs distant, perchance eons in the past. Orbital projections position 3IA Atlas along a route brimming with unrivaled viewing prospects, above all at its nearest pass by Mars on October 3rd. Such alignment arises no by chance. The interlopers' tilt in orbit and schedule mesh ideally for probe scrutiny precisely as terrestrial scopes forfeit visibility amid solar dazzle. Yet grasping the spectacle demands more than tracing 3I Atlas's provenance and destination. Deeper enigmas dwell in its responses to our star's rays, its inaugural brush with such illumination, and the stark deviations from anticipated patterns. Part 3. Trajectory and Timeline. The clock ticks relentlessly for 3I Atlas, and the observers hurrying to decode it ere it fades behind solar brilliance. Equations of celestial paths sketch an exacting itinerary across our system's heart, pinpointing pivotal moments that shape the insights humanity gleans from our third, affirmed interstellar sojourner. October 3rd, 2025 marks the inaugural pivotal juncture. Then, 3I Atlas will glide by Mars at about 30 million kilometers, some 19 to 0, 2 astronomical units. By stellar measures, this qualifies as an intimate brush, situating the far-roaming guest squarely within reach of sundry probes encircling the crimson orb. The juncture proves both auspicious and vexing in equal measure. Precisely as 3I Atlas attains peak proximity to Mars, granting orbital sentinels the sharpest glimpse of an extrasolar entity at work, Earth-based. As telescopes start to falter in following its path, the harsh rules of orbital dynamics draw the comet ever nearer to the sun's spot in our heavens, spawning viewing obstacles that will shortly prove impossible to overcome. Toward the end of October, on the nights of the 29th and 30th, 3I Atlas hits perihelion, swinging to its nearest point from the sun at about 1:36 to 1, 4 astronomical units away. That proximity situates it barely within the typical path of Mars, exposing this wanderer from beyond the stars to blasts of solar energy far fiercer than any it faced while cruising the Milky Way. Such scheduling aligns eerily well with the height of viewing woes as seen from our world. The progression of its pace unfolds a gripping tale all its own. Right now, speeding along at dozens of kilometers per second, 3I Atlas will surge to its top speed close to perihelion, possibly touching 68 kilometers, or roughly 152,000 mt. For context, our homeworld circles the sun steadily at around 30 kilometers. Thus, 3I Atlas will outpace our globe by more than double. Such rates of motion go beyond mere striking figures. They uncover the core principles driving travel across the stars. In contrast to bodies born in our solar system, which built their velocities via eons of pulls from the sun and its worlds through gravity, 3I Atlas bears the momentum gathered on its voyage amid stellar realms. Each kilometer per second of its rush stands for immense stretches crossed in the void between suns, shaped by the tugs of various stars in the galaxy's own spin. Its incoming route sets 3I Atlas alongside the ecliptic, that slim layer holding the bulk of our planet's loops. Such positioning eases the tight brush with Mars and sets up a far-off meeting with Jupiter come 2026. This setup of paths holds no accident. Incoming bodies from scattered angles in vast 3D emptiness would rarely skim so neatly past several worlds in their short sweep of our system. Worries over danger played no role in 3I Atlas's story, even though early scans tagged it as a possible risk. Its nearest pass by Earth comes at about 1:18 88 astronomical units, almost double the span to the Sun and far from any real peril. With NASA's nod on this secure gap, fears of impact faded from the public mind, freeing stargazers to chase knowledge instead of shielding our sphere. The true hurdle rests in the setup for watching. Spanning from October's start to November's dawn, 3I Atlas enters what experts term superior conjunction, a stretch where its sky spot from here hugs the Sun too tightly for useful sightings. The Sun-comet angle, known as solar elongation and measured from our vantage, sinks under 30 across much of this key phase. Picture hunting a dim glow bug right beside a blazing searchlight, and the spotting bind starts to click. No advanced scope can tease the weak shimmer of 3I Atlas from our star's blinding blaze when they crowd the view. This built-in barrier of ground astronomy ensures the comet's liveliest phase might slip by unseen to our eyes. The overlap in timing weaves a deep twist into the 3I Atlas saga. Right when the Sun's warmth peaks and the comet might unleash its wildest shifts, our watchers on Earth find themselves shut out. The height of gas release, likely splits, and fullest tail growth may all unfold in those spans when Earthbound instruments stand idle. This asignificant observational void underscores the vital role of probes scattered across the solar system, especially the ones circling Mars. Suddenly, the Mars Express and Trace Gas Orbiter from the European Space Agency, joined by NASA's Mars Reconnaissance Orbiter and MAVEN, step up as humankind's key sentinels for one of the decade's grandest celestial happenings. The schedule after perihelion brings a mix of optimism and pragmatism regarding potential sightings. If 3I Atlas emerges whole from its sun-grazing brush, ground telescopes on Earth ought to pick it up again come November or the start of December, once the angle from the Sun stretches past usable bounds. Yet by that point, the comet probably will have dimmed sharply, its volatile materials largely spent amid the unseen height of solar warmth. Forecasts for brightness indicate that, at peak, 3I Atlas stays a target solely for scopes viewed from our planet. Estimates for top luminosity sit between magnitudes 11 and 12, dim enough to evade unaided sight but accessible to gear used by backyard stargazers. While the absence of a dazzling bare-eye display might let down lay watchers, it in no way lessens the profound research worth of this one-of-a-kind clash with an extrasolar wanderer. The speed pattern highlights yet another key element in the 3I Atlas chronology. Nearing perihelion, the body's pace keeps ramping up thanks to the Sun's pull. Right after the tightest pass, though, that pull starts slowing the comet as it recedes from the solar hub. Such a shift in motion influences how long the intense heating lasts and the span for scrutiny from Mars-orbiting craft. Peering past perihelion, path projections depict 3I Atlas pressing onward across the solar realms, drawing near Jupiter by March 2026. Though this brush happens far farther off than the Mars skim, it could yield extra chances for probe views as the comet launches into its ultimate departure from our cosmic neighborhood. This schedule forges a tight slot of possibility unlike any astronomy has tackled previously. In contrast to recurring comets that loop back often for repeated exams, 3I Atlas grants just one shot to probe a relic from a distant stellar realm. Hurdles in viewing, alignment phases, and probe access all need to sync flawlessly if we're to pull the fullest insights from this stellar intruder. With the pivotal October moments nearing, the puzzle goes beyond what 3I Atlas might disclose of its nature. It's also if our watching tools can seize those disclosures effectively. Orbital math has locked in the itinerary, and it bows to nobody. Part 4, Coma, Expansion and Structure. What stuns most about 3I Atlas goes beyond its out-of-system routes or odd path. Rather, it's the vast, seemingly implausible envelope of air the thing is building enveloping it. Back in September 2025, NASA's SPAREX telescope spotted an anomaly that upended all prior frameworks for how comets act, a sprawling carbon dioxide coma reaching 348,000 kilometers out from the core. To fathom this span's enormity, picture how this spectral shroud spans about half our sun's width. The coma surrounding 3I Atlas has ballooned to envelop Mercury's full path, forming a vast sphere of vapors and particles that overshadows every standard comet halo seen in our system. Far from merely odd, this stands as a first in the records of cometary study. A coma arises as sunlight warms the frosts trapped inside a comet's heart, prompting them to vaporize straight from ice to vapor, skipping any melt. Imagine it like a starry ice lump hissing under solar rays. But the analogy, the portrayal undersells the ferocious intensity of this transformation. Icy substances sublimate violently into vapor, hurling tiny dust specks and hefty chunks into the void, thereby forging a swelling shroud that balloons to immense scales. The makeup of 3 Atlas's coma unveils origins shaped by environments wildly at odds with our own solar system's setup. Preeminence of carbon dioxide ahead of water vapor points to accretion in a zone favoring CO2 solidification over H2O, likely amid the chilly fringes of a foreign star's protoplanetary disk, where conditions kept carbon dioxide ice intact even as water lingered mostly airborne. Such a CO2-laden setting sheds light on the chemical milieu surrounding 3I Atlas's emergence. In contrast, most comets from our solar system feature water as the chief volatile, with carbon dioxide in a supporting role. The flipped proportions in 3I Atlas signal birth amid temperatures and pressures alien to bodies from our stellar locale. Yet the comet's makeup hardly stands alone as its quirk. Snapshots from the Hubble Space Telescope alongside Earthbound scopes expose formations defying core notions of comet dynamics. Rather than the standard tail drifting sunward, 3I Atlas exhibits what experts term an anti-tail, a spray of stuff seemingly aimed at the sun. This sun-facing feature poses a riddle that's robbed scientists of restful evenings. Standard comet mechanics hold that sunlight's push should drive fumes and grit away from the sun, yielding the iconic trails that have fueled tails across ages. Still, 3I Atlas defies this cornerstone, spewing matter along paths clashing with established lore. Hubble's July 21st views seized what team members labeled a forward gleam, a wedge-like form stretching from the core sunward instead of outward. Subsequent shots via the Gemini South Scope on August 27th depicted this odd layout holding steady and shifting, implying the anti-tail as the enduring trait over a fleeting oddity. The mechanics driving anti-tail emergence draw on intricacies surpassing mere photon shove. Bulky dust motes, hefty enough to resist easy solar nudges, might hold sun-directed paths if launched from the core with ample starting speed. Moreover, viewing angles can render three-way motion look sun-pointed from our planet's angle. That said, simulations falter in accounting for the endurance and boldness of 3I Atlas's sunward spray. The form seems overly crisp and enduring to stem from mere sightline tricks, while the dust sizes and launch speeds demanded for such a sprawling anti-tail strain comet core plausibility. Fresh scrutiny proposes the anti-tail arises from quirky spin patterns or crust traits peculiar to interstellar wanderers. A leisurely rotating core might sustain heat contrasts across lit and dark faces, channeling vapor bursts along targeted routes, or else 3I Atlas's outer layer could harbor stuff that reacts to sun warmth in manners strange to those versed in homegrown comets. The comas swell pace layers on further enigma. Spectral scans show fumes racing faster than norms for comets at matching sun distances. Such boosted venting might spring from ultra-fragile ices that endure solely in deep space chill. Upon initial encounter with intense sunlight, the nucleus starts vaporizing at an accelerated pace. Infrared data on the coma's gaseous content uncovers further irregularities. Readings of gas warmth from these scans indicate energy sources exceeding mere sunlight capture. Among potential causes are interactions among long isolated substances or the unleashing of power trapped in unusual frozen lattice formations that arose in the voids between stars. By combining perspectives from various sightlines and spectral bands, scientists have pieced together the coma's spatial form, revealing imbalances that indicate uneven vapor release from the core's exterior. Unlike the even halos common in thoroughly examined solar system wanderers, 3I Atlas exhibits streams and spreads of matter bursting from particular spots on its central body. Such streams imply that the core's outer layer holds isolated zones laden with easily vaporized substances, perhaps uncovered through collisions or heat fluctuations endured over the long voyage across interstellar expanses. This vapor release blueprint might retain clues regarding the comet's birthplace setting and its changes across countless years drifting through the cosmos. Examination of dust particles in the coma yields size ranges distinct from those in homegrown solar system icy bodies. The prevalence of sizable fragments needed to form the noted backward tail implies that 3I Atlas originated with altered dust-to-frozen ratios compared to nearby ones, or that its grains experienced alterations en route through the starless realms. The coma's outward spread exhibits shifts over time, aligning with the object's solar proximity and possibly its spin cycles. With 3I Atlas drawing nearer to its closest solar pass, the surrounding haze keeps expanding and shifting, liable to swell to greater extents amid rising solar warmth. Attempts to simulate the haze's upcoming development confront novel difficulties. The atypical makeup, backward tail shape, and boosted vapor emission levels all demand adjustments to conventional icy body dynamics theories. Experts are essentially crafting fresh conceptual systems on the fly, as fresh sightings keep exposing surprising traits. These consequences reach further than 3I Atlas alone. Should wandering star-crossers commonly show such odd haze features, it implies that our grasp of icy body science, drawn mostly from solar system locals, might cover just a limited range of potential actions. Every such outsider could compel overhauls to core ideas on their origins and developments. As 3I Atlas nears its key brushes with Mars and the Sun, the haze's ongoing swell and form changes will offer vital checks for rival explanatory schemes. Whether the sharpest shifts happen amid the viewing blackout when ground-based scopes lose sight of the wanderer remains an open query. Yet the haze's progression forms just part of 3I Atlas's overhaul under our star's rays. The standout visual alteration hit in mid-September as the whole entity lit up with a ghostly verdant sheen, hinting at reactions unseen before in any star-crossing guest. Part 5. Color Shift, the Green Glow. Midway through September 2025, 3 Atlas sparked waves of thrill across astronomy circles. It shifted to green, abruptly and boldly, via a bright jade radiance that turned this far-flung arrival from a dim blur into a seeming vital form amid the starry void. Amateur stargazers didn't spot the hue switch right away. 3 Atlas stays dim enough to evade unaided sight, yet advanced imaging gear on global observatories started recording shots displaying a vivid emerald hue enveloped the core of the comet. This shift stood out clearly in images captured amid the lunar eclipse of September 14th, where the Earth's satellite's umbra created deeper darkness, sharpening the visibility of the celestial body's fresh radiance. The verdant shimmer narrates a tale composed in the dialects of quantum physics and organic chemistry. Specific compounds soak up solar ultraviolet rays, propelling their electrons into elevated energy levels. Upon returning to baseline states, those electrons release photons at precise frequencies, which human vision interprets as particular shades. For 3I Atlas, this verdant output probably stems from diatomic carbon, a pair of carbon atoms linked as C2 per chemical symbols. In cosmic voids, diatomic carbon acts akin to a neon beacon on a molecular scale. Upon activation by the sun's UV rays, C2 units radiate at roughly 516 nanomi, yielding the signature emerald sheen that renders 3I Atlas among the most strikingly photogenic comets spotted lately. Known as fluorescence, this radiative mechanism converts unseen sunlight into detectable illumination, spanning vast distances in millions of kilometers to arrive at ground telescopes on our planet. Yet the narrative turns enigmatic at this juncture. Initial spectral scans of 3I Atlas revealed scant signs of carbon-bearing substances. Preliminary breakdowns indicated a makeup chiefly of carbon dioxide and water ice, featuring mere hints of the carbon rye elements usually linked to verdant hues in comets. Such a stark mismatch between the seen emerald radiance and the detected makeup has scientists racing to decipher the true dynamics in the comet's swelling envelope. A potential factor lies in alterations of the comet's vapor release patterns. With 3 Atlas drawing nearer the Sun and passing the 2 astronomical unit mark in early September, heightened warmth from the star could have started vaporizing hidden carbon reserves deep in the core. Such substances, sealed in the comet's depths over its extended voyage through interstellar space, may be encountering stellar rays for the initial occasion. The onset of the hue alteration aligns remarkably with the swift luminosity increase noted in mid-September. This implies that the mechanisms driving the surprising flare-up, perhaps a sudden ejection of gaseous elements from buried stores, likewise sparked the responses yielding the emerald output. Other theories for the tint alteration demand chemistry more intricate than basic diatomic carbon fluorescence. Celestial wanderers harbor scores of varied carbon-bearing compounds, each boasting unique radiative traits. The seeming emerald might arise from a mix of outputs from diverse types or from carbon-laden forms peculiar to deep space settings, absent in notable levels from comets native to our solar realm. Detection gear limits and data handling approaches further cloud hue assessments. Varied observatories, employing distinct barriers and capture setups, yield nuanced tonal depictions of identical targets. A feature seeming purely emerald in a single snapshot could seem cyan-tinged or ochre-leaning in the next, based on the exact bands captured and the ways those bands merge into composite visuals. The progression of the emerald radiance offers further hints into the core reactions. Diverging from the constant output anticipated in straightforward molecular fluorescence, sightings indicate the hue fluctuates in strength and spread across the head, with certain zones glowing more vividly emerald, implying carbon-bearing compounds distribute unevenly. Uneven dispersal of the greenish light permeates the broadening vapor envelope. Such irregularity in spread may stem from sporadic releases of gases, with streams bursting from particular spots on the core, hauling varied elemental makeups. On the other hand, this disparity could arise from alterations happening right in the envelope, where sunlight's UV rays dismantle intricate carbon-based compounds into basic pieces that shine at varied spectral bands. Moreover, this verdant radiance serves as a key indicator for probing the environmental states inside the envelope. The strength of the molecular shining hinges on the concentration of particles, their heat levels, and the potency of the sun's UV flux. Through tracking the shifts in this verdant shine as it moves away from the core and alters across durations, scientists can outline the spatial layout of the carbon-rich vapors in 3I Atlas's surroundings. Heat assessments pulled from traits of this verdant shine imply that the carbon-rich particles dwell in balanced warmth alongside the other envelope vapors. Such balance points to smooth swapping of energy among various particle types, offering clues about impact frequencies and flow behaviors in the widening aerial layer. The emergence of this verdant hue in 3I Atlas contributes yet another marker to the expanding list of contrasts between cosmic wanderers from afar and local solar realm bodies. 1I Oumuamua exhibited no evident traces of comet-like outbursts, hence no shifts in hue. 2 Boros showed typical comet shades, mainly from azure and pale diffused sunbeams instead of particle shine spectra. 3. I Atlas stands as the inaugural far-flung comet to form the traditional verdant envelope that backyard stargazers link to nearing regular comets. Yet, the exact spectral bands and power of this verdant shine might subtly diverge from known comets, possibly exposing elemental blends peculiar to bodies born near distant suns. The onset of this hue shift heightens the need for prompt watching. With 3I Atlas nearing its top alignment and slipping from Earth's view come early October, this verdant shine might keep developing or vanish altogether. The height of molecular shining typically hits close to closest solar approach when sun warmth peaks. However, this vital phase stays mostly veiled from ground scopes. Follow-on spectrum scans seek to pinpoint the exact particles fueling the verdant shine. Yet such scans demand big scopes and ideal viewing setups, which grow harder to secure as the comet nears the sun's blinding light. Every clear sky evening turns vital as sky watchers hurry to detail the shine prior to the target's disappearance. This verdant shine shift goes beyond mere eye-catching flare. It offers straightforward proof that 3IA Atlas faces deep elemental shifts upon meeting our sun's rays. The particles currently shining in the comet's envelope probably stayed inactive on a chemical level for eons, locked in icy quietude over the body's trek across stellar voids. At last, since its origin, 3IA Atlas now truly ignites as sun power sparks dormant reactions from its genesis near a foreign sun. This verdant shine signals the rousing of otherworldly reactions, the initial flickers of particle action in stuff shaped by settings perhaps wholly alien to our solar domain. Still, witnessing this rousing tests the edges of earthbound stargazing. The hurdles that will shortly compel experts to turn to robotic watchers scattered across the solar realm for ongoing surveillance of our transformed interstellar visitor. Part 6. Challenges in Observation. Cosmic forces display an ironic timing regarding 3I Atlas. Precisely when this cosmic wanderer starts unveiling its most captivating mysteries, the swift intensification, the improbable tail, the eerie emerald radiance, orbital dynamics align to pull it from the view of terrestrial watchers right at the pivotal phase of its path. Advanced professional scopes, outfitted with humanity's finest detection gear, encounter the identical core obstacle that plagues casual stargazers. Whatever lurks shielded by the sun's position stays invisible. While 3I Atlas advances steadily to its closest solar pass, its spot in our nighttime vault shifts relentlessly toward the blinding dominance of Sool, generating viewing hurdles that defy even the boldest tech innovations. The James Webb Space Telescope secured spectral scans of 3I Atlas on August 6th via its near-infrared spectrograph, yielding vital insights into its makeup chemistry, amid a rare interval when the planet's premier facility could aim at the comet sans peril of sun-induced harm. These scans offer among the finest chemical breakdowns achievable for such an extrasolar entity, yet they preceded the striking shifts of mid-September that elevated 3I Atlas from simply odd to profoundly enigmatic. The Hubble Space Telescope added its input on July 21st, snapping sharp photos that exposed the solar-directed jet formation and set bounds on the core's dimensions. However, fresh detailed visuals from key orbital platforms have grown scarce since August. Facilities equipped to deliver the in-depth scrutiny needed to decode 3I Atlas's odd traits are precisely those most exposed to solar disruptions as the comet nears alignment. Ground-based setups grapple with their share of layered issues. Varied instruments employing distinct filtering setups and alignment methods yield luminosity readings that frequently clash. Such discrepancies are commonplace in the field. Assessing luminosity, or photometry, demands meticulous regard for sky clarity, device tuning, and uniform protocols that differ across sites. The Comet Observation Database strives to bridge these gaps by gathering luminosity accounts from global spotters and graphing them alongside predictive frameworks. Across September, the compiled records plainly indicated 3I Atlas outshining forecasts, with recorded brightness levels steadily surpassing the anticipated line. But the spread in single readings mirrors the difficulties confronting watchers as they pursue a swiftly evolving target that upends their precise simulations. Hobbyists, typically relying on modest scopes and basic tools, supply essential extended surveillance info that elite facilities sometimes overlook. Still, their readings endure extra doubts from air currents, urban glow, and gear constraints. This yields a mosaic of sightings that together sketch an image of atypical conduct, even as each piece harbors sufficient ambiguity to spark arguments over the true events. The SkyEye and similar monitoring platforms assemble these varied inputs into luminosity profiles, tracing intensity shifts chronologically. Resources monitoring 3I Atlas reliably display the identical worrisome pattern, recorded intensity markers rising beyond the forecasted path, especially post-mid-September. Nevertheless, the exact scale of this divergence stays unclear owing to the built-in difficulties of gauging dim, swiftly varying the angle of solar elongation, defined as the apparent distance in the sky between 3I Atlas and the Sun from our planet's viewpoint, stands as the primary barrier to any viewing efforts. When this separation shrinks under 30 degrees, top-tier telescopes find it nearly impossible to distinguish the comet's dim glow from the diffused solar rays filtering through our air. Experts at major facilities usually halt their monitoring once it falls beneath 20 degrees, whereas hobbyists might spot the target vanishing sooner, hampered by gear constraints and site-specific factors. This progression of elongation sets an unyielding timer that earthly inventions cannot push back. Come the start of October, 13th Atlas slips under that 30-degree line where true viewing hurdles kick in. Around the middle of the month mid-October, the gap narrows to under 20 degrees, shutting down standard ground-level tracking altogether. Such obscurity lingers into the dawn of November, covering those vital days of peak solar warmth. The contradiction hits hard. Imagine peering at a starry spark drifting beside a blazing beacon, all with tools built to catch the subtlest gleams from far-off cosmic realms. Advanced setups like optics that adjust for air distortions or masks to eclipse starshine prove powerless against the core rules of sunlight diffusion, especially as the comet draws perilously near the sun's sky spot. Orbiting telescopes, in principle, hold edges over earthbound ones against sun-related disruptions, yet they grapple with built-in limits. Devices such as Hubble and James Webb feature safeguards that bar them from aiming near the sun, triggering autopauses during risky solar alignments. Vital for averting ruin to these multi-billion-dollar assets, such protections carve out blind spots right at the moments of greatest need. No worse schedule exists for 3i Atlas's solar approach than this for grasping its height of vigor. Simulations forecast the height of gas release, potential breakups, and the boldest tail formations clustering around perihelion toward October's end. Precisely these displays hold the keys to unlocking 3i Atlas's makeup, build, and roots, yet they'll unfold mostly shielded from our gaze. Handling data adds layers to the sighting woes. Shots of 3 Atlas demand meticulous refinement to isolate the comet's trace amid stellar clutter, radiation bursts, and device glitches. With the body dimming against the growing sky glow en route to conjunction, such refinements grow ever more vital and ever more likely to spawn flaws or fakes. Spectral studies, key to decoding the makeup in the comet's haze and streamer, demand stricter setups than mere light checks. Gear that splits the comet's rays into spectral bands thrives on vivid subjects under inky nights. As 3i Atlas dissolves in the sun's dazzle, chances for in-depth spectral probes evaporate exactly as the molecular frenzy might crest. Airy barriers hit various light bands unevenly. UV outputs, vital for spotting numerous compounds in comet comms, turn especially elusive with shrinking elongation, since our air bounces short blues and violets far more than longs reds. That very bounce, lending our heavens their azure hue, piles on hurdles for probing the reactions in 3i Atlas's swelling shell. As skies for watching worsen, linking up across sites turns indispensable. Facilities across various latitudes and time zones need to collaborate closely to make the most of the brief nightly viewing periods. Southern observatories in the southern hemisphere often maintain superior sighting angles for a bit more time compared to those in the north, which opens up chances for prolonged tracking that demands precise global teamwork. Variations in luminosity readings from phototrick instruments go beyond mere equipment shortcomings. They could also signal authentic fluctuations in the emissions from 3i Atlas. Comets frequently experience swift shifts in their glow from outbursts of gas, spinning influences, or alterations in the makeup of their cores. Separating instrumental inaccuracies from true changes in the comet grows harder as the signal-to-noise levels drop near the time of conjunction. Ground observations face extra complications from weather conditions. Clouds, air distortions, and typical seasonal patterns at key sites can wipe out vital viewing sessions that won't come around again. In contrast to recurring comets with reliable returns, 3i Atlas provides just one trip close to the sun, turning every cloudless evening into something invaluable and unique. The issue goes further than single sightings, touching on the larger matter of analyzing whatever data has been gathered. The pattern of luminosity where 3I Atlas surpasses forecasts might point to boosted gas releases, core modifications, or perhaps just flaws in the predictive frameworks employed for evaluation. Answering these puzzles calls for in-depth, sustained surveillance that's no longer feasible once the comet fades into the sun's blinding light. With terrestrial telescopes hitting their boundaries in tracking 3I Atlas, the duty for ongoing watchfulness passes to automated probes scattered across the solar system. Probes circling Mars, built for unrelated tasks, unexpectedly become humankind's main sentinels for one of the era's biggest celestial happenings. Part 7, the rising concern among astronomers. Beneath the precise wording of research articles and the tempered remarks in observatory updates, a wave of enthusiasm and, indeed, worry spreads among comet specialists around the world. 3I Atlas defies the established narratives shaped by years of comet studies, and experts are starting to concede, in their careful scientific manner, that they could be seeing an event without prior example. The luminosity pattern, recorded by watchers everywhere, amounts to far more than random fluctuations or recording mistakes. Diverse, separate monitoring setups, from the Comet Observation Database to dedicated hobbyist groups, reveal the identical disturbing trend. 3I Atlas steadily surpassing the estimates from conventional comet theories. The extent of this discrepancy, multiple magnitude steps brighter than anticipated, lies far beyond the usual allowances for citing errors. Dr. Matthew Knight, a comet expert dedicated to examining these bodies' actions over his professional life, pointed out in a recent discussion that the quick surge in brightness seen in mid-September questions core ideas about how volatiles escape in comets. The pace of that shift, he proposed, suggests mechanisms at work on timescales far quicker than the slow warming simulations commonly applied to forecast comet activity. Such scientific doubt sparks a unique thrill among the experts. They realize they may be encountering effects that demand fresh conceptual models to explain. Reports from Earth's telescopes on 3I Atlas highlight this strain, detailing sightings that keep astonishing the scientists even as they recognize that the peculiarities observed in this celestial visitor could stem from the erratic nature typical of bodies originating beyond our solar system. A distinctive plume oriented toward the sun sparks a fresh wave of intrigue among scientists. While backward-pointing tails are a familiar sight in comet studies, the enduring and striking forward jets of 3I Atlases challenge the limits of conventional theories. Experts are resorting to ever more unconventional hypotheses, such as peculiar dust particle properties, irregular spinning of the core, or rare combinations of ices, to make sense of actions that contradict established principles. One point of consensus among specialists is that 3I Atlas displays heightened vigor relative to ordinary comets at comparable solar distances. Observations from SphereX reveal a carbon dioxide-rich envelope stretching farther than ever recorded, implying release rates that far surpass expected norms. Such a shift isn't a minor anomaly from doctrine. Rather, it's a bold divergence calling for urgent clarification. Still, astronomers contend with the concept known as outburst bias, where short bursts of intensified output foster misleading views of ongoing oddity. These wanderers often experience abrupt flares in luminosity, only to revert swiftly to anticipated states. Lingering over 3I Atlas sightings is the dilemma of whether the September surge signals a true break from routine or merely a fleeting spike destined to diminish soon after. This ambiguity grows more acute amid the looming blackout in visibility. The pivotal phase for grasping 3I Atlas's essence. The interval encircling perihelion, marked by peak solar warmth, will unfold mostly out of sight from terrestrial scopes. Should the comet unleash its grandest shifts then, observers might forever puzzle over the September events without resolution. Dr. Carrie Halt, an investigator of extrasolar wanderers at the European Southern Observatory, voiced the widespread exasperation. The precise instant when 3I Atlas could unveil its deepest mysteries aligns with the stretch when ground-based viewing hits its lowest efficacy. She described this alignment as a universal plot thwarting discovery. Discussions reach past mere light readings into core inquiries about 3I Atlas as a material entity. Spectral breakdowns of its makeup display carbon dioxide to water ratios atypical for homegrown comets. Such variances may point to birthplace environments vastly unlike our own. Alternatively, they could arise from alterations sustained over eons of cosmic wandering. Enthusiast stargazers play a vital role in tracking 3I Atlas, delivering steady data that full-time facilities struggle to sustain non-stop. That said, the disjointed quality of hobbyist readings brings fresh hurdles. Varied watchers employing diverse gear and methods occasionally yield light estimates, clashing by notable degrees, complicating efforts to discern authentic comet shifts from observational glitches. Initiatives by the European Space Agency, managed via their Orbital Vigilance Initiative, seek to harmonize these conflicting figures even as they track 3I Atlas's path and illumination changes persistently. Their evaluations uphold the overall pattern of rising glow, yet highlight the hurdles in precisely gauging the extent. The comet's performance far surpasses what models had anticipated. Within astronomy's online forums, a blend of eager discovery and measured restraint defines the reactions to 3I Atlas. Experts post initial photos and luminosity readings, all while highlighting the doubts and constraints inherent in their findings. This approach indicates that investigators recognize the possible importance of their subject, yet hold back from hasty judgments, maintaining a disciplined doubt. A shift to green hues, recorded around mid-September, deepens the puzzle for scientists. Although emissions from diatomic carbon could account for the seen tint, the onset and strength of this emerald shine fail to align precisely with the molecular makeup revealed by prior spectral scans. Such a mismatch between chemical analyses and optical impressions points to either flaws in detection methods or dynamics in chemistry that outstrip conventional theories. Sessions at the American Astronomical Society's Division for Planetary Sciences gathering feature several discussions on 3I Atlas sightings and simulation-based analyses. Summaries from these show global teams striving to grasp not only the actions of 3I Atlas, but also the reasons behind the shortcomings of established frameworks in forecasting its actions. This pressing drive among scholars goes beyond mere inquisitiveness. It stems from an appreciation that chances to examine wanderers from beyond our solar system are exceptionally scarce. Having verified just 3 such cosmic travelers over all recorded time, everyone delivers priceless insights into environments around distant suns and the mechanisms shaping minor celestial bodies across the cosmos. As the time frame for viewing tightens, global partnerships have ramped up. Observatories across Chile, Hawaii, the Canary Islands, and Australia synchronize their watches to ensure broad surveillance, while 3I Atlas nears the alignment with the sun that will halt everyday ground observations. Every site brings distinct strengths, ranging from sharp detail photography to tailored spectrum analyzers, aiming to pull the most knowledge from the fading chances to observe. Astronomers in the field also wrestle with conveying information to the wider audience about 3I Atlas. News outlets occasionally amplify the confidence in research outcomes or dramatize elements of the comet's conduct that specialists admit are ambiguous. Managing fascination with this uncommon outsider against the built-in ambiguities of active studies demands precise handling of result disclosures and understandings. Frameworks for evaluating threats from near-Earth rocks gain fresh scrutiny regarding 3I Atlas, not due to any peril it presents to our planet, but owing to its erratic patterns, underscoring gaps in knowledge about how compact objects react to sunlight's warmth. Should experts struggle to forecast 3I Atlas's path reliably, it raises concerns over the trustworthiness of systems applied to gauge dangers from additional bodies. The growing buzz over 3I Atlas captures a core truth in advancing knowledge. It underscores how the universe repeatedly yields events richer and more unexpected than our concepts can foresee. With October drawing near and terrestrial views growing ever harder, stargazers pin hopes on probes scattered through the solar realms to seize the insights that surface instruments must forgo. Part A, the Mars Pass, emerges as a prime prospect. As our homeworld gears up to have 3I Atlas vanish amid solar brightness, a neighboring realm readies for prime viewing of the spectacle. One of the premier celestial happenings in contemporary astronomy stands out prominently. Come October 3, 2025, the red planet will stage humankind's nearest brush with an extrastellar guest, granting probes circling Mars exceptional chances to scrutinize 3I Atlas from a perspective that ground telescopes on our world could scarcely aspire to match. The alignment proves ideally serendipitous. While 3I Atlas glides by Mars at about 30 million kilometers away, equivalent to some 0.2 astronomical units, various probes active in the Martian sphere can redirect their sensors at this stellar wanderer. Such sightings occur mere days prior to the superior conjunction that renders Earth tracking unfeasible, forging an essential relay from ground to orbital surveillance. ESA's Mars Express orbiter, sent aloft in 2003 and operational well past its planned duration, bears the high-resolution stereo camera responsible for charting Martian landscapes with remarkable precision across more than 20 years. Though crafted for geological surveys of worlds, HRSC holds the acuity and finesse to possibly record intricate views of 3I Atlas's core and the dense inner layers of its coma. Dr. Colin Wilson, serving as project scientist for the ExoMars Trace Gas Orbiter, has stated that teams are assessing prospects for the Color and Stereo Surface Imaging System, or CASIS, along with the NOMAD spectrometer standing for nadir and occultation for Mars discovery, to target the interstellar object. Meant for probing Mars's air makeup and land traits, these tools may discern molecular traces in 3I Atlas's broadening coma. NASA's Mars Reconnaissance Orbiter offers some of the most compelling prospects for in-depth scrutiny. Its High-Resolution Imaging Science Experiment, or HiRISE, regularly snaps features under 1 meter in size from an orbit hovering around 300 kilometers over Mars. Even though 3I Atlas approaches from a greater remove, HiRISE's superior clarity could unveil nucleus formations on the comet hidden from terrestrial scopes. The MAVEN probe, NASA's endeavor for Mars' atmosphere and volatile evolution, equips spectrometers tailored to dissect air chemistry and motions. Such features might yield key insights into the makeup of 3I Atlas's coma, especially the CO2-heavy vapors that define its spectral profile. Yet these viewing windows bring formidable engineering hurdles. Every Martian satellite got built and tuned for examining the planet up close, not chasing swift entities amid the stars. Guidance mechanisms, tuned for a vast close-by body, require adjustment to pursue a tiny remote quarry hurtling at cosmic speeds. The core barrier lies in signal intensity. At peak nearness to Mars, 3I Atlas will register as profoundly dimmed gear meant for local planetary work, not far-flung voids. With an anticipated brightness of magnitude 12 to 14 amid its flare-up, the comet strains the thresholds of typical orbiter imagers and analyzers. Dr. Wilson highlighted these constraints in latest exchanges with global stargazers, observing that though sightings of 3I Atlas from Mars hold promise in concept, the true yield hinges on elements like the object's glow at periapsis, the planet's weather state, and the precise setups needed for accurate aiming. Mars vantage points offer perks surpassing mere nearness. The sightlines from Mars amid the October 3rd pass by viewing the interstellar visitor, 3I Atlas from Martian vantage points, offers insights impossible to gain from our home planet. The positions relative to the Sun, specifically, the angles formed by the Sun, the comet, and the watching spacecraft, vary greatly when seen from Mars compared to Earth, which could uncover aspects of the surrounding dust envelope and the tails form that stay concealed from ground-based scopes on our world. Interactions between the solar wind and this object open up yet another domain where satellites circling the red planet could deliver one-of-a-kind data. As 3I Atlas brushes against the solar wind, that relentless outflow of ionized particles from the Sun, it may trigger effects that the plasma sensors and magnetometers on various Mars probes can pick up. Such encounters hold the potential to disclose clues regarding the object's core makeup via shifts in its electromagnetic characteristics. Efforts by the European Space Agency to synchronize observations during the Mars Close approach demand extraordinary teamwork among probes built for wholly unrelated research goals. The Mars Express craft, meant initially for probing the planet's crust and air layers, now doubles as a watcher of extrasolar wanderers. Meanwhile, the Trace Gas Orbiter, tuned for spotting methane and analyzing air molecules, has to reconfigure its tools for examining comet light signatures. Planning these views gets trickier due to strict time limits. Probes around Mars stick to fixed timetables for everyday scans of the world below, links back to Earth for signals, and upkeep tasks on the hardware itself. Slotting in sessions to track 3I Atlas demands precise juggling to sidestep clashes with core tasks, yet sees the best chances for discovery. Sending the gathered info back poses major hurdles. These orbiters link up with Earth only in set periods when the paths of the two worlds align just right for clear radio signals. Pictures and light analyses of 3I Atlas have to vie with standard data from planetary studies for the scarce channel space, which might push back the sharing of findings for weeks or even months. Backing these orbital watches from the surface calls for teamwork across global space outfits and science hubs. The European Space Operations Center in Germany, along with NASA's Jet Propulsion Lab in California and various other sites, need to collaborate on sequencing the looks, handling the flood of raw info, and spreading the outcomes to scientists everywhere. If these views from Mars pay off, they could reshape our grasp of 3I Atlas in profound ways. Sharp pictures might pin down the core's dimensions and outline with new accuracy, putting to rest arguments over its bodily size and build. Light-splitting studies could spot chemical building blocks that escape detection from earthly instruments, exposing makeup details that hold echoes of where and how the comet took shape. Fine points about the dust halo and streaming tail, especially that odd spike aimed toward the sun that stumped experts, could sharpen into focus from the red planet's special angle. Variations in the sun relative viewing angle might clarify if the backward-pointing tail stems from real material flung sunward, or if it's just an optical illusion that shifts with different sightlines. Still, it's wise to temper hopes for what these Martian watchers can deliver. In the best scenarios, the haul from such efforts will probably amount to just a few snapshots and light profiles, not full-blown ongoing surveys. The gear aboard was crafted for other purposes entirely, so its power might fall short of tackling the big riddles about 3I Atlas's essence and actions. Whether it works out hinges on factors no one can steer. Should 3I Atlas flare up brightly again before October 3rd, that could make it visible enough for the Mars orbiters to catch. Devices that might typically deem it too dim for detection could now capture it clearly. On the flip side, should the comet dim from its present heightened luminosity, the most hopeful viewing plans could still produce zero valuable insights. Humanity's prime chance to keep watch over 3I Atlas lies in the Mars close approach, especially amid those vital days when ground telescopes on Earth can no longer track this star-born wanderer. While Earth-centered stargazing gears up for a forced quiet spell stretching into early November, the robotic sentinels circling Mars provide the sole prospect of beholding what could turn out to be the most thrilling segment of 3IA Atlas's brush with our star system. Regardless of whether these sightings thrive or flop, they signal a fresh era in humanity's pursuit of extrasolar travelers, showcasing our advancing skill in syncing watches from various planets, all while these targets zip by at speeds from distant stars. Part 9. Superior Conjunction and Disappearance. The equations governing sky paths show no regard whatsoever for people's inquisitive minds. With October advancing and 3I Atlas pressing onward in its unyielding path sunward, the spatial truths of path dynamics align to yank our cosmic outsider from view right at the moment it could unveil its deepest mysteries. Superior Conjunction, the phase where 3I Atlas sits too near the sunspot in our heavens for feasible viewing turns one of the grandest sky spectacles in living, recall into a stellar sleight of hand. The schedule advances with unyielding accuracy. Come the start of October, 3IA Atlas slips under 30 solar elongation. That's the limit where major viewing hurdles kick in for Earth surface scopes. Sunlight's air diffusion generates a glowing celestial backdrop that drowns out the weak glow from our far-flung guest. Expert facilities, armed with advanced distortion-correcting tech and vast light-collecting might, manage to stretch their watches a bit beyond what hobbyist gear allows. Yet even those pros confront mounting despair in the conditions. Around mid-October, the separation shrinks to under 20, putting an end to standard ground checks. The comet doesn't vanish in a flash. Instead, it dims bit by bit against the sun's blaze, much like a dawn star, growing harder to spot until spotting it shifts from tough to outright undoable. Such a slow shift complicates nailing down the precise instant when our planet bids farewell to 3I Atlas visually. Still, the end effect stays unchanged. Our main glimpse into the comet's actions shuts tight precisely as sun warmth nears its fiercest peak. The conjunction span carries on into early November, covering about 4 to 5 weeks during which 3I Atlas stays all but unseen from Earth. Far from just an annoying break in data flow, this spells the total cutoff of our tracking powers over the comet in the stretch that simulations forecast as its height of frenzy. Top gas releases, fullest tail growth, likely breakup incidents, and further striking happenings might all unfold out of mortal sight. The bitter twist sharpens in light of 3I Atlas's latest antics. The swift glow-up seen in September, the odd backward tail form, and the striking emerald hue all point to a body facing course shifts under our sun's energy onslaught. Reason suggests these shifts ought to ramp up with rising solar warmth, possibly hitting dazzling peaks close to perihelion toward October's close. However, that closest solar pass hits right in the heart of the conjunction window, when 3I Atlas hugs nearest the sun from Earth's vantage, and viewing turns utterly unfeasible. The schedule proves disastrously off, for glimpsing the genuine transformation of this cosmic wanderer under peak sunlight exposure proves elusive. One might think the cosmos conspired to hide the climax of this spectacle from view, shrouded like a performance veiled by stage drapes. Superior conjunctions mechanics harbor no plot to thwart research progress. Instead, they stem purely from the orbital geometry of watching from a world that circles the identical sun as the subject. With 3 Atlas nearing its sun-closest point, the comet's skyward-seeming spot inevitably draws nearer to the solar disk. That visual gap narrows progressively, leading to the icy body seeming to slip astern of our central star, yielding viewing hurdles that even cutting-edge tech cannot surmount. Experts in stellar tracking encounter such barriers routinely and vexingly when probing items venturing near the sun's realm. Orbiting platforms dedicated to solar scrutiny, such as the Solar and Heliospheric Observatory known as SOHO, occasionally follow comets amid these alignment phases via coronagraph tools that obscure the sun's glare. Yet 3 Atlas's path stays too distant from the sun to register on those dedicated detectors, which usually spot entities mere solar radii away from our star. This alignment-induced void poses novel hurdles for researchers habituated to unbroken surveillance tools. Contemporary celestial science depends profoundly on prolonged watch programs that follow targets across full activity phases. Icy wanderers especially demand prolonged scrutiny to separate fleeting flares from enduring shifts in conduct. The imposed break in watching amid 3IA Atlas's pivotal phase rules out such thorough examinations. Probes scattered across the solar realm present scant substitutes for terrestrial sightings, though their functions stay bound by initial setups geared toward world explorations over comet pursuits. The Mars-based craft mentioned before offer the best short-range chances, yet their glimpses amount to fleeting captures instead of the steady oversight essential for grasping 3I Atlas's progression. The European Space A's Bay Colombo endeavor, en route to Mercury now, traces a course that could yield sporadic views of 3I Atlas from angles unlike those from our planet. Still, the probe's gear suits Mercury probes best, and the setup needs for icy body tracking might clash with the venture's routine limits. NASA's Parker Solar Probe, built to probe the sun's outer atmosphere and particle streams, maneuvers deep in the solar interior, potentially brushing against 3I Atlas's tail or coma remnants in theory. That said, the craft's stretched oval path and emphasis on solar events over comet ones curb its value for routine icy body tracking. This alignment stretch likewise hampers simulation work aimed at forecasting 3I Atlas's actions. Digital recreations of comet dynamics draw on site data to tune forecasts and confirm reliability. The 4 to 5 WE span without sightings strips away vital markers that simulators require to sharpen insights into this extrasolar body's reaction to stellar warmth. Once terrestrial views restart come November or December's dawn, 3I Atlas will probably have altered profoundly compared to the form skywatchers noted in September. The comet could glow more intensely, perhaps sprouting dazzling tail formations catchable by hobbyist scopes. Or it could dim markedly should its fleeting ices exhaust amid the unseen sun grays. Even more strikingly, 3I Atlas could have split apart into several fragments at its tightest solar brush. Comet 3I Atlas draws nearer to the solar vicinity. Fragmentation events for such bodies prove frequent around perihelion, as gravitational pulls from tides and heat-induced pressures surpass the fragile bonds securing the nucleus's components. Should such a split happen amid conjunction, terrestrial viewers must grapple with the difficulty of spotting and following several fragments once visibility returns. Observations restarting in late November or December demand meticulous strategy and global collaboration between facilities. Upon exiting conjunction, 3I Atlas will appear in an unfamiliar celestial sector, compelling instruments to search out and recapture the wanderer following an extended blackout. Alterations in its luminosity, location, and form could render recognition and pursuit notably arduous. Public fascination with 3I Atlas encounters distinct hurdles tied to this alignment. Reporting on celestial phenomena usually depends on striking visuals and ongoing reports to hold viewer captivation. The imposed quietude spanning the conjunction halts the flow of fresh sightings that fuel widespread curiosity, possibly dimming enthusiasm precisely when the comet undergoes its profoundest shifts. Teaching prospects encounter setbacks in this observational void as well. Classrooms and hobbyist stargazing circles frequently leverage vivid comets to instruct on orbital mechanics and viewing methods within the solar realm. 3I Atlas's plunge into blinding solar light strips away these chances during potentially its most captivating phase, where tail formation and core outbursts might yield the richest visual lessons. This alignment phase underscores the inherent bounds of stargazing, even after ages of instrumental progress. Observers stay tethered to their native world for the bulk of cosmic scrutiny, beholden to spatial alignments dictated by our planet's stance against targets in the star. Not even our advanced orbital observatories can fully evade these barriers when subjects venture excessively near the sun's locale. With 3I Atlas fading into solar brilliance, experts gear up for an interval of conjecture and simulated projections drawn from partial records. The issue at hand goes beyond mere alteration during its concealed transit. Rather, it concerns if those evolutions will prove interpretable upon renewed scrutiny, or if the alignment interlude will spawn enduring enigmas regarding events in the pivotal stretch of this extrastellar guest's solar passage. Part 10. Perihelion Anticipations. Concealed deep in the overwhelming solar radiance that obstructs earthly scopes, 3I Atlas readies for its fateful rendezvous. Across October 29th to 30th, 2025, this star-spanning nomad attains perihelion, its minimal solar distance at roughly 1.36 to 1.4 astronomical units. Shielded from mortal gaze, the comet endures solar energy barrages unprecedented in its multi-million-year trek among stellar domains, perhaps sparking evolutions that reshape insights into rogue celestial entities. The velocity progression itself narrates a tale of interstellar ferocity. Presently, hurtling at dozens of kilometers per second, 3I Atlas nears peak swiftness by perihelion, possibly surging to 68 kilometers, or about 152,000 mph. For perspective on this phenomenal pace, note that our world circles the sun at around 30 kilometers. 3I Atlas will outpace our globe by over double, hauling momentum amassed over its grand galactic voyage. Scientific principles foresee perihelion igniting the climax of 3I Atlas's solar immersion, with solar warmth cresting at utmost levels. As the comet's core heats up dramatically, it could trigger the release of dormant volatile materials that endured unchanged during its long journey through interstellar space. Simultaneously, frozen water, carbon dioxide, carbon monoxide, and various rarer solidified gases might start turning directly into vapor, sparking a massive swelling of the surrounding haze that could surpass the extraordinary scale seen back in September. Heightened emissions from the surface may generate striking streams of dust bursting out from specific spots on the central body. Such streams arise when buried volatile reserves carve out routes to the surface, forming arching sprays that stretch several thousand kilometers outward. The enigmatic tail pointing toward the sun, which has baffled watchers, could grow much more pronounced, or fresh tail formations might appear as assorted volatile elements join the haze for the initial time. Models in theory indicate that 3I Atlas's abundance in carbon dioxide could lead to actions at closest solar approach unlike those of ordinary comets from our solar system. Since carbon dioxide vaporizes more easily than water ice under the anticipated heat levels close to perihelion, this might yield gas output levels far surpassing those from water-led comets by wide margins. Such boosted vigor may show up through swift shifts in luminosity, haze extent, and tail configuration, unfolding across mere hours instead of the usual days or weeks in comet development. The threat of breaking apart casts a veil of doubt over forecasts for perihelion. Among the solar system's most delicate bodies, comets cling together via feeble gravity and the cohesion of their frozen frameworks. The heat pressures from fierce sunlight, paired with the physical strains from bursting emissions, can shatter these holds and rip the cores asunder. Breakup incidents often happen with startling abruptness. A comet, seeming solid as it nears perihelion, might divide into several fragments in just hours, driven by uneven heating that weakens the build, or by gas bursts that dig out inner material from the core. Should 3I Atlas undergo such a split, ground observers on Earth will confront the challenge of spotting and following numerous pieces once viewing restarts in November. Past cases of comet breakup near perihelion offer vivid instances, such as Comet Shoemaker-Levy 9, which shattered from Jupiter's gravitational pull before crashing into the planet in 1994. In more recent times, Comet Ison crumbled amid its perilously tight solar pass in 2013, leaving a swiftly scattering rubble trail as it receded from perihelion. Yet breakup remains far from certain. 3I Atlas's durability hinges on elements like core makeup, inner porosity, spin speed, and the precise heat strains from its distinctive volatile blend. As interstellar wanderers, these objects may hold build traits markedly unlike solar system comets, rendering them either tougher or more prone to heat-induced failure. The pace of 3I Atlas's rush through perihelion further shapes the odds of breakup. In contrast to comets that hover long at their solar nearest, 3I Atlas will hurtle by swiftly thanks to its hyperbolic path. This brisk transit shortens the span of maximum warmth, possibly easing the total heat burden on the core. Should 3I Atlas emerge whole from perihelion, the phase afterward promises a body reshaped by its brush with blazing solar energies. The haze could balloon to greater scales as top emission rates spread substances over vast new expanses, fresh molecular types freed from hidden reserves beneath the surface. Signs of intense internal warming might first show up in spectral data gathered from afar. Shifts in hue, extending past the familiar green glow that's been noted, could emerge when various molecular forms start to shine under the sun's UV rays. If intricate organics lurk inside the core, they may shatter into basic pieces that glow at signature wavelengths, possibly sparking a full spectrum of colors in the light we see. The backward tail feature, seen in all 3I Atlas sightings so far, could shift wildly close to closest solar approach. Boosted release of dust might form several tail formations aimed variously, since bits of differing scales react uniquely to the push from sunlight. Such arrangements could yield key details on the core's spin speed, outer makeup, and inner build. Examining dust specks gains special weight around that solar nearest point. The spread of sizes and makeup in bits flung from the core mirror the inner layout and birth settings of the prime body. Bigger chunks may point to a crumbly core full of big empty spots, whereas tiny powder might hint at a tighter build or certain makeup traits that boost tiny bit creation. The charged fields and gas surroundings by solar closest add fresh twist to 3I Atlas's actions. Outflowing sun-wind ions clash with charged vapors in the comet's halo, sparking tangled electric-magnetic effects. Such clashes may speed bits to swift paces, spark seen shines in the halo, and shape the growth of gas tails stretching millions of kilometers after the core. Heat readings at solar nearest, grabbed via probe views if possible, might offer core truths on 3I Lace's heat traits and inner setup. Varied easy melt stuffs turn to gas at set heat levels, making a chem gauge of the warm-up flow. Solar rays pierce the core's outer skins. What follows closest solar pass hinges sharply on the stock of easy melt goods in 3I Atlas and how well that stock can flee via the core's skin. Bodies rich in easy melt stores may keep up strong outbursts for weeks or months post-closest, whereas ones short on such goods might dim fast as their outer skins empty out. Pull tugs from the sun's strong pull field at solar nearest may tweak 3I Atlas's later path too. Though the comet will surely head out along its open curve route, tiny speed shifts could tweak when and how it meets far solar realm worlds, especially Jupiter, come 2026. The solar nearest trek marks the peak of 3I Atlas's solar realm brush, that instant where eons of space between stars' growth clashes with the fierce ray zone around our sun. Be it flashy bursts of starfire shows or subtle shape shifts tucked in a swelling halo, the closest pass will deeply reshape 3I Atlas from the arrival body in our solar realm to a fresh, never-seen form. The puzzle lingering for sky watchers over the alignment phase is if 3 Atlas will step out from its veiled solar nearest trek as the familiar form that gripped viewers in September, or wholly remade by the rawest sunray clash. The truth stays veiled in sunblaze, biding the steady orbit's layout to uncover the closest pass's handiwork. Part 11. Contrasts with earlier interstellar arrivals. Grasping the importance of 3I Atlas and its peculiar motions requires a retrospective scan of the concise yet transformative chronicle of verified cosmic intruders from afar. Just a pair of entities preceding this latest arrival stand confirmed as hailing from outside our solar system, with each reshaping the pages of celestial science through its distinctive traits. Their combined narrative unveils a tapestry of stellar variation that upends long-standing notions regarding the conduct of these nomadic heralds dispatched from remote stellar realms. 1I Oumuamua burst onto the scene, first detected on October 19, 2017, via the Pan-STARRS Panoramic Survey Telescope and Rapid Response System stationed in Hawaii. Deemed an asteroid at outset owing to the absence of any apparent coma, Oumuamua swiftly demonstrated how interstellar wanderers defy terrestrial anticipations. Its profoundly stretched form, approximately 400 nanometers in length and 40 meters across, bore no resemblance to any prior asteroid or comet catalogued within our solar domain. Adding to the enigma, Oumuamua displayed anomalous non-gravitational propulsion while receding from the sun, gaining velocity in manners defying pure gravitational pull. Such enigmatic thrust ignited discussions that persist to this day. Could it stem from vapor release by concealed volatile reserves, sunlight's radiative push on an oddly configured body, or perhaps an unconventional phenomenon stretching the limits of established physical laws? The lack of any observable coma encircling Oumuamua clashed with projections for bodies harboring the icy volatiles common to comets. Nevertheless, an undeniable influence was evidently at work, driving the noted speed-up. The proposed explanation, insofar as one exists, relied on outgassing so faint it evaded detection limits, yet sufficient to nudge Oumuamua's path. 2I Borisov, spotted on August 30, 2019, by hobbyist stargazer Gennady Boris in Crimea, unveiled an altogether contrasting character. In stark opposition to its forerunner's cryptic antics, Borisov struck as reassuringly conventional upon initial review. It embodied a textbook comet featuring a hazy coma and emerging tail formations aligning with predictions for solar-warmed visitors. That said, deeper scrutiny exposed how Borisov's surface familiarity concealed molecular makeup alien to comets born in our solar neighborhood. Spectral data highlighted carbon monoxide levels far exceeding those in homegrown comets, hinting at origins in a protoplanetary disk marked by distinct thermal and compositional slopes compared to our solar nebula. Borisov's coma also showed a dust-to-gas proportion at odds with solar system standards, pointing to either divergent birth mechanisms or alterations accrued over its cosmic voyage. These understated yet profound molecular variances offered the inaugural concrete proof that alien stellar nurseries forge comets bearing signatures of their singular genesis settings. Enter 3I Atlas into this rarefied league, bearing attributes that render its antecedents appear almost routine. The coma laden with carbon dioxide, spotted by SphereX and validated by subsequent scrutiny, marks the sharpest chemical rift from solar system baselines among all known interstellar guests to date. Analysis from the James Webb Space Telescope on the CO2 to water vapor proportion points to even stranger natal circumstances than those shaping Borisov. The anti-tail of 3I Atlas, oriented toward the Sun, finds no counterpart in records of earlier interstellar encounters. Whereas Oumuamua lacked tail features from its seemingly negligible outgassing, and Borisov sported standard comet tails trailing sunward, 3I Atlas forges a configuration that upends foundational comet dynamics. Centuries of careful skywatching have molded our grasp of physical laws. A sharp surge in luminosity, noted back in September 2025, contributes one more striking trait to the ever-lengthening roster of peculiarities linked to 3I Atlas. Oumuamua and Borisov never displayed such intense fleeting shifts in shine, pointing to dynamic forces at work in 3I Atlas, perhaps bursts of released gas, shifts in its framework, or alterations across its outer layer that unfold far quicker than the paces seen in other interstellar drifters examined before. When we stack up their scales, compelling trends emerge among these far-flung cosmic intruders. Oumuamua's form, gauged at about 446 meters, dwarfs the usual pint-sized space rocks while falling short of the hearts of most bustling comet heads. For Borisov, the central body's width, clocked at roughly 1 kilometer, slots neatly into the everyday measurements for comets circling our Sun. Gauging 3I Atlas's dimensions throws up hurdles that echo the deep mysteries cloaking its core identity. Scans from the Hubble Space Telescope point to a central width ranging from 0.32 to 5.6 kilometers, a span that spans from petite comet cores to ones of middling heft. That vagueness springs from the tough task of peeling apart the heart from its sprawling, misty envelope. Such a standout quality alone carves 3I Atlas apart from the earlier wanderers from the stars. Tools for probing chemistry have leaped forward markedly from one interstellar find to the next, opening doors to ever sharper probes of their inner workings. Oumuamua's fleeting stint in sight, paired with scant gas releases, boxed in the breakdowns to mere surface gleam traits and ballpark mass per volume figures. Borisov's standard comet-like antics open the way for light-splitting scans to pick out steam, carbon monoxide, and a host of other tiny chemical clusters. With its hazy shroud echoing those of comets, 3I Atlas draws on the sharpest watching gear ever turned toward a star-hopping body. Infrared light dissections via the James Webb Space Telescope, crisp snapshots from Hubble, and earthbound scopes fitted with cutting-edge light splitters deliver matchless clarity on its makeup, form, and shifts through time, right down to its path around the Sun. Every trait of these star-crossing guests spins its own yarn about the galaxy's restless flows and the upheavals that hurl remnants from their natal stellar homes. Oumuamua swung into our solar realm from the vicinity of Vega, yet its trek outlasted that star's entire lifespan, hinting at a tangled route weaving through galactic expanses. The leftover zip it kept after slipping the Sun's tug, known as hyperbolic excess velocity, hit about 26 kilometers. Borisov's course traced back to a zone teeming with fresh blazing suns in Cassiopeia, carrying an excess velocity of around 32 kilometers. That brisker pace signaled a launch from some beefier stellar cluster or a speed-up via gravitational nudges along its star-spanning voyage. 3I Atlas boasts the swiftest such excess velocity recorded for any interstellar arrival, pegged at roughly 39 kilometers. That blistering pace evokes origins near an outsized star or a series of gravity-assisted boosts amid its galactic ramble. Such momentum also shapes its antics at the sun's nearest point, where quicker rushes cut short the window for solar warmth to burrow into the depths of its heart. The spans between spotting these interstellar passers yield glimpses into their galactic numbers. Just 2 years separated Oumuamua from Borisov, then 6 more elapsed before 3I Atlas, implying these drifters sweep past our central solar zones with steady rhythm, yet evade easy notice thanks to their compact builds and lightning-fast glimpses. Statistical analysis of the 3 observations from the trio of verified extrasolar wanderers reveal that everyone embodies a distinct mechanism for crafting minor celestial bodies, implying vast variation in the ways alien solar systems generate and launch icy and rocky fragments instead of settling into standard traits. Every fresh arrival from beyond our system has broadened the spectrum of potential actions and makeup. Distinctive traits of 3I Atlas, including its record-breaking coma expanse, backward-pointing tail formation, molecular makeup, and light output changes, point to a breadth in extrasolar body variety that outstrips predictions from models drawn solely from our own system's history. Every such arrival imparts fresh insights into world-building dynamics across the cosmos, even as it sparks fresh inquiries into the array of undiscovered extrasolar bodies lurking out there. While 3 Atlas navigates its concealed trek nearest the Sun, stargazers must merely ponder if its reveal after alignment will inject fresh oddities into the expanding roster of extrasolar body quirks. The trajectory set by Oumuamua and Boris implies that 3I Atlas will keep astonishing experts with actions that upend core beliefs about the dynamics of tiny space rocks. The core takeaway from these 3 extrasolar arrivals is that the cosmos fashions minor bodies via mechanisms far richer and more intricate than anything at play in our home stellar neighborhood. Every such body bears traces of its chemical and physical origins from 2 SAW environments that stand in stark contrast to our familiar stellar surroundings, offering unfiltered glimpses into the developmental arcs of planetary setups scattered across the Milky Way. Part 12: Scientific Unknowns and Active Debates. The astronomy world's reaction to 3I Atlas unfolds like a mystery tale in which vital proof stays concealed, compelling experts to weave explanations from fragmentary hints as the key details lurk obscured by the sun's blinding light. Various rival theories strive to account for the comet's odd conduct, yet every proposed solution breeds additional riddles that could linger unresolved barring fresh sightings after alignment to supply the absent elements of this cosmic enigma. The dispute over the core's dimensions and form highlights the core obstacles confronting 3I Atlas investigators. Data from the Hubble Space Telescope has refined the dimension guess to a span of 32 to 6 kilometer across. Yet this wide span underscores the hurdles in distinguishing the dense core from its vast surrounding haze. Such ambiguity counts heavily, since dimensions shape estimates of weight, compactness, exposed expanse for gas release, and endurance under the fierce warmth near the sun. Varied assessment methods yield clashing outcomes. Heat simulations drawn from infrared data propose a tinier core boasting high albedo, meaning a shiny exterior that bounces back solar rays with ease. Optical spectrum scrutiny points instead to a bigger, gloomier core that soaks up more stellar energy. This clash might stem from shifts in outer layer makeup, errors in gauging, or deep gaps in grasping how 3I Atlas handles solar warmth. Breakdown of its makeup grapples with its share of inconsistencies. Spectral scans via the James Webb Space Telescope pinpoint carbon dioxide as the leading gas in 3 Atlas's haze, where CO2 levels surpass water steam by wide margins. Such a profile stands in sharp relief to typical comets in our system, which usually feature water as the chief gas reserve. Still, the prevalence of carbon dioxide poses hurdles in rationalizing further noted features. The emerald hue that emerged in September usually signals release of diatomic carbon. But CO2-rich outgassing doesn't naturally. Scientists fail to identify the carbon-containing compounds that cause the green fluorescence in this object. Either the spectral examination overlooked key chemical elements, or the emerald hue stems from mechanisms far more intricate than basic molecular glowing. Terrestrial spectrum studies conducted with the extremely large telescope and additional facilities. Prominent astronomical sites have identified extramolecular types, such as cyanide-based substances and diverse organic entities. Such findings point to a chemical intricacy surpassing the mere prevalence of CO2 noted in orbital surveys, implying that 3I Atlas harbors a varied collection of elementary and elaborate carbon-rich materials. The anti-tail configuration offers the greatest enigma among the observed features. Standard comet dynamics require that sunlight's radiative force drives gases and particles outward from the star, forming appendages that extend directly opposite the solar position. Yet, 3I Atlas defies this core rule by expelling substances that shape formations directed sunward instead of anti-sunward. Dr. Keto and Dr. Loeb's latest theoretical examination, now in peer evaluation, contends that the anti-tail emerges from atypical size ranges in dust grains paired with particular launch angles from the core's exterior. Their framework posits that sizable dust fragments released toward the sun with adequate starting speed can resist radiative expulsion, yielding the noted sun-pointing formations. That said, rival theories draw on alternative physical processes. Certain experts argue that electric influences, namely clashes between ionized dust and stellar magnetic lines, might steer particles into unforeseen paths. Additional hypotheses claim that 3I Atlas's spin orientation generates heat imbalances that focus vapor release in targeted zones, irrespective of radiative forces. The spin cycle of 3I Atlas stays undetermined after extensive monitoring over many months. Photometric profiling, which tracks luminosity shifts from an uneven core tumbling under solar illumination, has not uncovered distinct rhythmic patterns. This lack of evident spin markers might signal extremely leisurely turning, an almost round form, or spin intricacies that mask straightforward cyclic shifts. Spin condition impacts numerous facets of comet activity. Fast-rotating bodies encounter outward forces that alter vapor emission layouts and form endurance. Leisurely turning comets build thermal contrasts across illuminated and shadowed faces, channeling sublimation of ices to warmed areas. The mysterious spin traits of 3I Atlas hinder attempts to simulate its heat progression and forecast subsequent actions. The luminosity changes recorded in September pose their unique analytical hurdles. Various tracking arrays verified that 3I Atlas grew markedly more luminous than models anticipated, though the extent of this outlier sparks discussion. Certain watchers describe intensity surges matching multiple magnitude steps, whereas others propose subtler boosts consistent with typical comet fluctuations. These variances stem in part from observational constraints. 3I Atlas lingers close to the sensitivity thresholds of typical scopes, rendering precise light measurement tough even in ideal setups. Diverse teams employ varied reference stars, color filters, and data processing methods that may embed biases in luminosity assessments. At a deeper level, the scarcity of prior records hampers pattern evaluation for brightness. In contrast to recurring comets tracked across repeated visits, 3I Atlas stands as a one-time encounter with no past benchmarks for reference. Investigators thus depend on scientists rely on conceptual frameworks derived from comets within our solar system to predict typical patterns, yet such frameworks might fail to account for entities originating from distant stellar setups. Efforts to pinpoint origins involve reconstructing the path of 3I Atlases backward across the galaxy, aiming to pinpoint its likely starting point. Recent examinations of its motion point to an emergence from the Milky Way's thin disk, that expansive star-packed layer where the bulk of ongoing stellar births take place. Still, the doubts surrounding its recorded spot and speed amplify as they extend into the past, yielding ever-widening uncertainty zones that span various potential origin zones. The puzzle of its galactic roots bears directly on decoding 3I Atlas's makeup and timeline. Items hurled from nascent stellar clusters could preserve unique elemental markers compared to those from aged, advanced cosmic settings. The prevalence of carbon dioxide might stem from its genesis in a nascent planetary disk marked by varying heat levels and molecular distributions. Diverging from the formations yielding solar system bodies, the firmness of its build sparks ongoing scholarly contention. The broad envelope and backward-pointing tail imply intense vapor release, possibly signaling a core abundant in fleeting substances or one facing breakdown. Certain experts argue that 3I Atlas embodies a fragile aggregate of minor fragments, a heap of debris sustained by faint gravity pulls, prone to shattering amid heat or gravitational pulls. Other theories view 3I Atlas as a single solid body, featuring odd exterior traits or inner makeup responsible for the noted vapor emissions. This divide holds key for forecasting actions close to closest solar approach when heat pressures and pulls hit their peak. The abrupt surge, noted at 2 astronomical units in early September, stays largely unexplained. The sharp rise in vigor as 3I Atlas passes this solar range may point to the triggering of certain fleeting materials that turn to gas at set heat thresholds. Or else, it could signal shifts in the core's framework, unveiling hidden stores of volatiles to sunlight exposure. Varied fleeting types vaporize at distinct solar separations, forming an inherent progression of triggers. Nearing closest solar point, ice from water starts major emissions near 3 astronomical units, whereas carbon dioxide persists functional far beyond. The unique patterns of 3I Atlas hint at an intricate blend of fleeting substances whose trigger points diverge from norms seen in solar system comets. The viewing blackout amid alignment adds further doubt regarding which conceptual setups most aptly describe 3I Atlas's actions. Vital checks of rival ideas, such as the comet's reaction to peak solar warmth, sites of any breakup, shifts in emission flows, will unfold mostly out of sight from ground telescopes. As 3I Atlas reappears post-alignment in late November, experts must grapple with assessing views of a body potentially altered profoundly in its unseen closest solar trek. Its look after alignment might affirm existing conceptual setups or spawn fresh riddles demanding wholly novel accounts. The scholarly clashes around 3 Atlas echo the wider hurdle of grasping events that arise seldom and strain detection tools to extremes. Every reading bears doubts, every framework rests on premises, and every reading needs to weigh the chance that interstellar bodies follow natural laws unseen in solar system encounters. Part 13. Natural Explanations. Before venturing into the domain of outright conjecture, scientific rigor insists on exploring every unconventional yet feasible natural account for the perplexing actions of 3I Atlas. Though this comet defies our present comprehension in striking ways, it probably adheres to established physical laws, just functioning amid circumstances so intense that humanity has yet to witness them. The prevalence of carbon dioxide identified in 3I Atlas's coma offers an initial insight into its extraterrestrial character via standard comet studies. That makeup implies it originated in a zone of its home stellar setup where heat levels stayed cool, sufficient for CO2 to solidify into frozen form, even as water stayed mostly gaseous. Such setups generally arise past the boundary astronomers term the carbon dioxide snowline, marking the stellar distance at which CO2 shifts from gas to solid. Within our own solar setup, this CO2 snowline sits far beyond the Sun compared to zones birthing most comets. That accounts for why local comets feature water as their chief volatile element, with carbon dioxide in a minor supporting part. Yet, alien stellar realms might display varied heat patterns, star brightnesses, or elemental mixes that position the CO2 snowline amid key comet-building zones. A star dimmer than our Sun could shift the carbon dioxide snowline nearer the core, enabling CO2-heavy comets to emerge in orbits mirroring those yielding water-led bodies here. Or, a star bearing altered elemental makeup, say, carbon boosted against oxygen might yield nascent planetary disks favoring CO2 buildup over water frost, temperature aside. This origin scenario idea not only unpacks 3I Atlas's odd elemental profile, but also its boosted gas ejection patterns. At equal warmth, carbon dioxide turns to gas more easily than water frost, possibly yielding emission speeds that outpace water-led comets by wide margins. Such stepped-up eagerness to vaporize might justify the swift glow-up seen in September, alongside the coma scale unmatched before, as caught by Sphere-X. Still, the CO2-loaded makeup by itself fails to decode the sun-facing countertail that has baffled watchers from the debut of close-up views. Here, dusty plasma dynamics steps in, bringing mechanisms blending rigid body motions, fluid flows, and electric-magnetic interactions. Solar UV light-striking coma gases sparks ionization, birthing plasma, a brew of charged bits sensitive to pulls of gravity plus electric-magnetic influences. This charged haze couples with electrified dust bits through intricate paths, spawning ordered patterns far from what basic gravity or light push theories foresee. Electrified dust bits might weave into flows, threads, or twisting shapes under the sway of solar winds' embedded magnetic pulls. In certain setups, these electric-magnetic forces could trump light pressure, letting stuff drift in paths seeming to defy core comet rules. Outcomes might include countertails aimed sunward, even as standard tails drift oppositely. The dusty plasma account strengthens when factoring 3I Atlas's ramped-up gas emissions. Denser gas clouds foster greater chances for sparking and particle charge swaps that heighten electric-magnetic impacts. Its quirky elemental mix could further shape plasma buildup via molecules that spark easier or at altered paces than norms from solar system comets. Spin's condition presents yet another path to unpack 3I. Applying standard physical principles to harsh environments sheds light on the peculiar actions of 3I Atlas. An inner core spinning at a leisurely pace might generate notable heat disparities across its illuminated and shadowed halves, focusing the release of gases into particular zones instead of spreading them evenly over the entire exterior. Should 3I Atlas turn so gradually that its sunlit portion climbs to much warmer levels than those faced by comets in our solar system, then swelling from heat and built-up vapor forces might propel streams of substances outward at speeds sufficient to push back against the sun's radiative push facing inward. Such dynamics would favor expelling matter sunward from the warmest spots on the core's outer layer. To support this idea of sluggish spinning, one must account for the reasons 3I Atlas deviates in its turning from the norm seen in ordinary comets. Bodies drifting through the void between stars undergo unique developmental paths on their voyages from one stellar neighborhood to another. Encounters with cosmic grit, tugs from gravity during close stellar flybys, or tangles with magnetic influences might tweak spin patterns in manners absent for items bound to a lone star's domain. The emerald hue emerging in September poses distinct hurdles for straightforward interpretations. Swan bands from C2 molecules usually yield that verdant glow in a comet's envelope, yet early spectral scans revealed scant signs of carbon-rich compounds beyond CO2. Still, the idea of a critical boundary posits that C2 emission ramped up markedly only after 3I Atlas passed a key heat or sunlight intensity mark around 2 astronomical units away. This boundary phenomenon might stem from the solar UV rays splintering CO2 into CO and O atoms. Subsequent UV splitting of CO could then free the carbon nuclei needed to form C2 pairs. Achieving this demands precise light exposures and particle concentrations, possibly missing from 3I Atlas's first sightings, yet emerging as it drew nearer the sun's path. Another pathway for carbon reactions draws on intricate organics lingering in minute amounts inside the core, yielding visible signals solely under targeted stimulation setups. Things like PAH, amino acids, or varied organics might fragment amid fierce sunlight to release carbon-laden bits that shine at verdant frequencies. Differences in the outer layer's makeup provide yet another everyday rationale for 3I Atlas's odd traits, sidestepping the notion of an even core blend. The entity could feature separate patches with distinct elemental profiles, certain zones loaded with CO2, others packed with H2O frost, and more sheltering elaborate organics. With 3I Atlas nearing the sun and fresh areas of its skin warming up initially, such makeup shifts might spawn evolving gas release schemes. The early sway of CO2 could mirror the swift rousing of the easiest to vaporize outer layers, whereas prolonged warmth might uncover deeper stuff with altered builds. The degree of sponginess and inner makeup likewise shape how comets act, offering clues to 3I Atlas's quirky features. A core riddled with voids, basically a flimsy aggregate of frost and grit bound by faint bonds, might permit sunlight's warmth to burrow far inside, stirring hidden vapor sources usually shielded from outer shifts in climate. This boosted sponginess notion accounts for the vast envelope and swift flares and shine. Probing warmth deeper stirs bigger batches of vapor stuff than usual in denser comet cores, yielding vapor output paces that outstrip forecasts drawn from mere outer layers. Solely relying on thermal effects falls short. The voyage of 3 Atlas across vast distances between stars may have induced alterations in its framework, unlike anything faced by bodies within our own solar system. Exposures to cosmic rays, collisions with interstellar grains, or fluctuations in temperature amid varying radiation fields might reshape the core's traits, affecting how it reacts upon reaching a star's fierce glow. What best accounts for the remarkable actions of 3I Atlas likely stems from these environmental forces working in tandem. Its abundance in CO2 fuels vigorous sublimation. Dynamics in plasma give rise to peculiar backward tails. A leisurely spin focuses outbursts in certain zones, while intricate reactions yield the noted shifts in hue. Though every such mechanism aligns with established principles of physics, their interplay amid the harsh realities of an extrasolar wanderer's approach can spawn effects that seem utterly implausible when viewed against the backdrop of familiar comets from our system. 3. I Atlas might embody a comet of deep eccentricity, not an outright extraterrestrial oddity, yet this eccentricity positions it as the ideal specimen to upend our grasp of minor celestial mechanics across the cosmos. Part 14. Exotic and Fringe Theories. Here we step into realms where imaginative tales converge with bold conjecture, dissolving the lines between ordinary cosmic events and wildly improbable accounts. Though solid proof eludes these outlandish views of 3I Atlas's behavior, the object's singular traits spark the very musings that have shadowed every baffling sky event in humanity's past. Such notions serve not as rigorous scientific proposals, but as mental probes that reveal the sheer oddity of our star-hopping guest as it truly is. Among exotic notions, the idea of an alien tech signal stands out as the enduring favorite for quirky sky wanderers. From the moment one Ayum Muammua's find ignited talks of crafted beginnings, every fresh extrasolar arrival stirs whispers of engineered traces. The swift surge in luminosity, odd backward tail, and bolstered haze around 3I Atlas might, in theory, signal startup routines for an autonomous device tuned to stellar energy fields. In this signal concept, 3I Atlas appears as a slumbering engineered relic, lying quiet through its epic trek between suns to safeguard energy and form, only rousing when hit by stimuli that launch built-in startup routines. That September flare-up could signal the point where sunlight hit the threshold to awaken idle mechanisms. Meanwhile, the backward tailform might hint at focused beam outputs or substance releases tied to some engineered function. Yet this engineered angle crumbles swiftly against the weight of actual sightings. Scans from the James Webb Space Telescope and Earthbound scopes reveal unmistakable traces of commonplace icy gases, carbon dioxide, water steam, and carbon-based stuff, all fitting the profile of routine comet venting. Nothing shows odd isotope mixes, synthetic substances, or power patterns linked to cutting-edge tech. Pushing deeper into wild conjecture, the notion of a pseudobiotic plasma draws from studies of intricate plasma actions that can form apparent order in niche setups. Lab trials have shown that grainy plasma's blends of ionized bits and tiny solid flecks can arrange themselves into forms displaying traits echoing those of living setups. Plasma structures of this kind possess the ability to replicate, adapt, and react to shifts in their surroundings in manners that superficially echo the traits of biological entities. Certain scientists have pondered whether intricate plasma arrangements could emerge spontaneously amid cosmic settings, possibly exhibiting actions that imitate basic lifelike patterns. The peculiar emission behaviors, backward-pointing tails, and dynamic luminosity shifts observed in 3I atlases might, in theory, embody expressions of these plasma-driven occurrences. This notion of vitalized plasma implies that the void between stars could host organizational modes governed by laws of physics utterly distinct from those underpinning carbon-centric life. Such imagined beings could lie inactive across voyages through the interstellar medium, only to stir upon nearing the magnetic fields near stellar bodies, generating visible outcomes that imitate yet fail to embody genuine vital functions. Nevertheless, this account demands reliance on physical processes that exist solely in conjecture. Although grainy plasmas do assemble elaborate configurations in controlled lab settings, extending such events to the scale of comet-like bodies navigating the solar breeze calls for leaps well outside established knowledge. Observers find no signs indicating that 3I Atlas displays the electromagnetic markers anticipated from vast plasma assemblies. The Deliberate Explorer storyline recasts 3I Atlas as a deliberate probing endeavor originating from a remote stellar domain, equipped with scripted actions intended to examine our Sun's domain as it traverses the closer zones. Under this view, the object's odd traits appear as deliberate attributes. Its broad enveloping haze could serve as a means for detection or signaling reach, whereas the reverse tail formation might function as apparatuses for sending information to far-off collectors. According to the Explorer idea, 3I Atlas's surge in light stems not from haphazard releases, but from deliberate engagement of monitoring and messaging setups as the entity nears its core objectives. The schedule of maximum vigor close to Mars and at closest solar approach may signal planned inspection routines instead of mere reactions to stellar warmth. Such a reading sparks fanciful musings on 3I Atlas rousing itself amid the energetic imprint of our solar neighborhood, its engineered awareness awakening following eons of quiet passage through starless expanses. The verdant hue could signal the startup of inactive detectors, as swift variations in glow might point to computations and broadcasts in progress. Still, the Explorer tale encounters identical proof-related hurdles as the signal transmitter theory. The molecular traces, heat responses, and form details of 3I Atlas align with projections for commonplace bodies, though atypical variants. Nothing points to computation handling, aimed signaling, or further pursuits typical of engineered setups. The unusual substance theory posits that 3 Atlas harbors substances or functions via physical rules beyond present comprehension. Concepts in advanced physics outline options for strange matter types bearing odd traits, engagements with unseen mass, altered pull forces, or subatomic influences acting across large dimensions that might yield sights-defying routine physical laws. Strange substances might account for 3I Atlas's odd reverse tail via pull irregularities that alter substance paths, or justify its boosted emissions via power liberation paths exceeding standard reactions. The quick luminosity rise could mirror peculiar state shifts or power-holding devices guided by as-yet unveiled physical tenets. Such ideas open the door to extraordinary natural events that surpass what science grasps today, implying that 3I Atlas embodies organic mechanisms rooted in physical laws unfamiliar to human knowledge. It might act as an unplanned testing ground for probing laws of physics that fail to appear in the standard setups of terrestrial experiments. Speculations about time-based oddities plunge into the wildest realms, proposing that 3I Atlas could embody a kind of data or substance movement spanning vast timelines in the cosmos. Fictional tales in science envision the comet functioning as a dispatch or relic dispatched from humanity's tomorrow, propelled rearward via methods that evade the usual limits of cause and effect. Under this view, 3I Atlas's peculiar traits stand as signs of time-altering forces instead of journeys across stellar distances. Perhaps the entity hails from an advanced iteration of our solar setup, bearing data or substances meant for this era. Its odd conduct may stem from clashes between tomorrow's inventions and today's environmental realities. Yet, ideas of time meddling demand a framework of physics that's not just unverified, but clashes head-on with core tenets of cause-effect logic and heat dynamics in their present form. Observations yield no hints that 3I Atlas breaches preservation rules or shows time quirks exceeding the routine speed-induced shifts anticipated for swift-moving bodies. A skeptical lens on these far-out theories underscores the frequency with which seemingly baffling sky events gain everyday rationales after enough detail surface. Early pulsar finds stirred talks of crafted pulses from superior societies, yet they turned out to be swiftly spinning collapsed stars. Quick radio pulses ignited comparable discussions prior to linking them to ordinary cosmic happenings. Past patterns indicate that 3 Atlas will eventually gain a rationale inside established physics, even if it taps into unseen mechanisms or settings. The comet's distinctive features probably mirror the vast array of environments in distant stellar realms, not signs of rare physics or crafted devices. The worth in delving into these hypothetical paths rests not on their likelihood, but on how they spotlight the sheer marvel of 3A Atlas against the backdrop of our stargazing legacy. Something capable of prompting deep thoughts on extraterrestrial devices, animated energy forms, and bizarre substances signals a truly novel element in our grasp of spacefarers from afar. While 3I Atlas pursues its concealed trek past the sun's nearest point, such outlandish theories remind us of the immense gaps in our cosmic awareness outside our home system. Be it that the comet reappears from alignment as a plain yet quirky item or keeps showing traits that defy standard accounts, it has already broadened the edges of possibilities for interstellar wanderers. Part 15, Countdown and Implications. Countdown and the universe's timer advances to key instants that will shape not just 3I Atlas's self-disclosures, but the lessons it imparts on the wider array of drifters amid the stars. Every approaching benchmark poses a vital trial for our comprehension, our watching tools, and our skill in drawing solid insights from events that strain the edges of modern sky-watching methods. October the 3rd, 2025, signals the initial pivotal point, 3I Atlas's nearest pass by Mars at roughly 30 million kilometers. This encounter, this offers humankind's prime chance to keep watch over the cosmic intruder as terrestrial observatories start to forfeit their view of it. Orbiting instruments around the red planet will push for sightings outside their planned scopes, pushing engineering limits to snag photos and spectral data from a body hurtling by at speeds from beyond our stars. Achievement hinges on factors outside our grasp. Should 3I Atlas hold steady or boost its present luminosity, those Martian satellites could grab sharp views of its core makeup and tail movements unseen by ground instruments. But should the icy wanderer dim after its September high, the finest onboard detectors may pick up just faint traces too weak for solid research. Toward the end of October comes the unseen peak of its closest solar approach, spanning the 29th to 30th at roughly 1:36 AU from the star's core. In those vital hours, 3IA Atlas faces heat and light blasts that may spark the wildest shifts in its whole trek through our system. Peak warmth could rouse dormant gases locked since its star-crossing voyage, possibly sparking vapor bursts grand enough to reshape the wanderer's basic traits. Still, that solar nearest point hits right when 3I Atlas turns hardest to spot from our world, lost in the sun's blinding haze that no Earth telescope can pierce. The universe's twist puts peak curiosity exactly at the low point of our watching power. Any secrets from that close past stay mostly out of sight, saved just in stray clues left for future study. The viewing blackout stretches into November's start, forming a 4 to 5 week stretch where 3I Atlas slips fully from our sight. Such unwilling quiet hits amid model forecasts of the wanderer's liveliest stretch, which might include breakups, wild light shifts, or matter changes that usually draw heavy watching efforts. Surfacing again by December's dawn marks the coming key turn as the angle from the sun widens enough for ground scopes to find and follow 3I Atlas post its blind spot. The body rising from that solar hideout could look worlds apart from its October fade, perhaps marked by splits, huge glow changes, or shifted makeup echoing its brush with fierce sun warmth. After that solar dip, the schedule opens research windows into the next year and further. The swing by Jupiter in March 2026, though far looser than the Mars brush, could yield extra craft views, while 3IA Atlas starts its last outbound leg from our realm. The setup might enable far-off peaks from probes such as Juno or the upcoming Europa Clipper, based on their work state and path setups. Insights from strong sightings reach well past the quirks of 3I Atlas alone. Probing its star-born makeup yields raw bits from stuff born near distant suns, holding clues to matter setups in young system clouds across the cosmos. The spotted high carbon dioxide load points to birth spots far from our own sun's birth cloud, implying system building blocks differ more than once thought. Watching comet actions in harsh settings may upend ideas on gas bursts, speck motion, and charged gas flows. The study of physical processes in alien cosmic settings reveals how the anti-tail feature in comets disrupts core beliefs regarding the interaction between cometary substances and sunlight, possibly demanding fresh conceptual models that incorporate magnetic field influences overlooked by standard approaches. Such findings carry wider ramifications for inquiries into celestial wanderers from beyond our solar system and their contributions to molecular transformations across the Milky Way. 3I Atlas stands as merely the third verified interloper from a foreign stellar realm, yet its peculiar traits imply that our galaxy possesses vastly greater variety in the genesis of minor celestial bodies than existing hypotheses anticipate. Every such extraterrestrial visitor examined yields vital information for gauging their prevalence and the insights they offer into environments around remote suns. Examination of breakup dynamics. Should 3I Atlas undergo disintegration near its solar closest point, it might yield groundbreaking revelations about the inner makeup and material layering of interstellar wanderers. Varied pieces could hold substances from multiple layers of the primordial core, essentially offering drill-extracted specimens from a body birthed near a different star. Patterns of piece scattering along with compositional variances might uncover architectural secrets unattainable through views of whole entities. Handling expectations demands recognition of the built-in constraints when probing items that linger just at the edge of visibility, even in ideal scenarios. 3I Atlas probably won't turn into a visible wonder for ground viewers on our planet, as top luminosity projections linger near magnitude 11 to 12 accessible via telescopes, yet hidden sans viewing tools. While the absence of a striking sight show in no way reduces its research worth, it certainly curtails chances for widespread public involvement, which frequently fuels sustained support and enthusiasm for space science endeavors. The forthcoming Comet Interceptor effort by the European Space Eye, set for liftoff toward the end of the 2020s, marks an effort to build quick reaction tools for probing freshly spotted interstellar intruders. In contrast to classic probe voyages needing prolonged preparation for set goals, Comet Interceptor will linger in orbit at the Earth-Sun L2 Lagrange location pending an apt candidate's arrival, at which point it will veer off to rendezvous and examine the intruder amid its journey through our system. That said, Comet Interceptor's potential stays hampered by the core issue of spotting interstellar wanderers soon enough to permit probe rendezvous operations. 3I Atlas surfaced just months prior to its nearest solar pass, leaving too little window for tailored probe ventures, regardless of whether fast reaction setups were available. Upcoming spotting technologies need to pinpoint such cosmic guests years ahead to make worthwhile probe meetings feasible. Enhancements to Earthbound scanning efforts promise nearer-term gains for advancing the field of interstellar intruder research. Now building in Chile, the Vera Rubin Observatory plans to start functioning in the mid-2020s, boasting unmatched wide-sky monitoring prowess. Its capacity for frequent snapshots of vast sky regions might catch interstellar wanderers far sooner during their system traversals, granting longer viewing windows and superior chances for in-depth analysis. The main task of the Rubin Observatory, known as the Legacy Survey of Space and Time, anticipates uncovering interstellar wanderers at a pace of a few annually after complete startup. This sharp rise in spotting rate will shift interstellar intruder investigations from sporadic lucky glimpses to organized group analysis capable of tackling key issues surrounding the galaxy's stockpiles of small bodies and their molecular development. Advances in adaptive optics, spectroscopy, and orbital platforms, ongoing efforts in observation, are steadily broadening the horizons of insights gained from dim and swiftly traversing objects such as 3 Atlas. Upcoming advanced giant telescopes, among them the 30-meter telescope and the European Extremely Large Telescope, promise enhanced light collection and finer detail resolution that might utterly transform the analysis of interstellar visitors. The James Webb Space Telescope's strengths in infrared detection have already proven invaluable for probing interstellar objects, yielding details on chemical makeup unattainable through earlier tools. Prospective orbital platforms, tailored for examining minor bodies, might deliver unbroken surveillance free from terrestrial air distortions or alignments with the Sun. As studies of interstellar objects demand synchronized viewing from diverse sites and regions, global collaboration grows ever more vital. The 3I Atlas Monitoring Initiative has showcased the promise alongside the hurdles in rallying worldwide efforts toward fast-shifting celestial phenomena. Insights gained from this collaborative push will shape subsequent handling of comparable finds. Protocols for exchanging and scrutinizing data crafted during 3IA Atlas viewings are setting benchmarks for the astronomy field in managing swift, urgent phenomena that demand prompt input from various observing sites. Such guidelines will grow indispensable with rising detections of interstellar objects and more chances for joint examinations. Impacts reach further than stellar science into core inquiries on substance and molecular makeup across the cosmos. 3. iAtlas offers tangible proof of environments in distant solar setups, kept intact over eons of voyage through the void. Every datum aids in grasping variations in world-building mechanisms amid varied star surroundings. Probes into life's origins arise from these interstellar probes, since such wanderers could carry carbon-rich molecules or basic biological entities from one stellar realm to another. Though nothing indicates 3IA Atlas contains living substances, its carbon-based makeup might reveal patterns in elaborate organic distributions galaxy-wide. Spotting proteins, genetic building blocks, or further life precursors in such drifters would deeply affect views on how essential life ingredients disperse via the cosmos. 3I Atlas's distinctive molecular profile, though lacking direct ties to biology, shows how interstellar drifters maintain intricate structures over vast cosmic spans. While planetary protection issues don't apply to 3I Atlas given its harmless path, research on interstellar drifters refines knowledge of their reactions to sun warmth. Subsequent cosmic intruders could trace paths nearer our world, necessitating precise forecasts of their actions for collision hazard evaluations. The odd traits of 3 Atlas expose flaws in existing simulations for forecasting icy body actions, implying defense frameworks need to include variants unfamiliar from local solar origins. Deeper grasp of interstellar drifter dynamics might turn critical for properly gauging dangers from later arrivals that could truly endanger us. Chances for involving the public around 3I Atlas capture the difficulties and gains in sharing frontier knowledge with everyday viewers. The icy body's intricate details and low brightness pose obstacles to widespread casual appeal. Still, its origins beyond our system and peculiar actions stir enthusiasm in those aware of its importance. Schools across the globe are weaving observations of 3I Atlas into their lesson plans. By treating the comet as a live demonstration of breakthroughs in science and advancement, learners get to track ongoing observation efforts, examine open-access datasets, and observe the shifting landscape of knowledge as fresh findings come to light. The private sector in space exploration is displaying growing enthusiasm for research on minor celestial objects, appreciating their importance for knowledge and the prospective financial gains from assessing asteroids and comets. Although 3I Atlas offers zero prospects for extraction or mining because of its hyperbolic path, the methods honed in its examination enhance overall skills for evaluating compact cosmic entities that could hold commercial promise as those key October milestones draw near. 3I Atlas has effectively proven that objects from interstellar space will repeatedly upend our preconceptions regarding the feasible within the cosmos outside our own solar realm. If the comet's subsequent actions validate existing models or spawn wholly fresh enigmas, it has set a fresh benchmark for the astonishing in celestial events. The ultimate defining element of 3I Atlas's enduring impact hinges on the insights gained from scrutiny in the vital period to come. 3I Atlas is starting to unveil its genuine essence, a preserved repository of chemistry originating from another stellar domain, a stellar system elsewhere, an experimental site for physics functioning amid unprecedented environmental factors, or maybe an even greater marvel that compels a total revision of our grasp on entities drifting amid the stars. Over the coming weeks, it might erupt in dazzling luminosity never seen, break apart into a shower of cosmic fragments from afar, or glide silently beyond our star, bearing its enigmas into the vast emptiness. And any outcome might profoundly alter our perspectives on arrivals from distant suns. The invitation to join this interstellar investigation rings loud for all who can engage. Keep an eye on photo dispatches from ESA's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN. Then, anticipate the after-perihelion reports from Hubble Space Telescope and James Webb Space Telescope, which could at last disclose the authentic nature of 3I Atlas. The cosmos has delivered an envoy from a foreign star, and soon we shall decipher its tidings.